Hello, and welcome to the full course session on Multibody Dynamics using SolidWorks, an essential tool for simulating motion and dynamics in mechanical systems. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can now proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're dedicated to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and techniques. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, you will be introduced to motion study in SolidWorks through the design and simulation of a Geneva mechanism. We'll explore different types of Geneva mechanisms and learn how to model and assemble an external Geneva mechanism. You'll also perform a motion study on it, plot the contact forces between the parts, and post-process the simulation to derive insights. Specifically, you'll learn the basics of modeling and assembling in SolidWorks, pre-processing the model for motion analysis, and post-processing to obtain results as plots. In the second chapter, you will work with a machine vise. You will learn how to model and assemble the machine vise and understand the role of screw mates in motion studies. You'll perform motion studies to trace the displacement of the movable jaw, giving you hands-on experience with SolidWorks' motion study tools. The key focus will be on understanding screw mates and how to trace displacement within a mechanical assembly. In the third chapter, we'll dive into the design and MBD simulation of a planetary gear train. You will learn gear terminology, how to import standard gears into SolidWorks, and how to conduct motion studies to understand speed and torque variations. You'll also explore the application of gear mates in these complex systems. By the end of this chapter, you'll have mastered the basics of gear terminology, speed and torque variation, and the application of gear mates. In the fourth chapter, we will explore the kinematics of an IC engine piston assembly. You will design the assembly, simulate its motion, and learn how the wrist pin offset affects piston displacement. You'll also assign materials to the parts and understand how they influence the simulation. This chapter will provide a detailed look at IC engine kinematics and the effects of material assignment. In the fifth and final chapter, you will focus on the design and MBD simulation of an IC engine valve train. You will learn how to model the valve train, calculate cam lift, and design the cam accordingly. We'll also study the effects of springs in the valve train, discussing the damping coefficient and the free length of the spring. By the end of this chapter, you'll understand how to model a cam based on valve lift specifications and analyze the performance of the valve train under dynamic conditions. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievements on LinkedIn. Let's get started with Multibody Dynamics using SolidWorks.
Hey guys, hope you're doing good. Today we are going to be learning how to simulate the multibody dynamics of a Geneva mechanism. So in a Geneva mechanism there are two primary parts, the driver and the driven part. The driver part is the one on the left hand side, whereas the driven part is on the right hand side. The driver part is connected to a motor which basically makes it rotate, and this motion is transferred, and that's what we are going to be simulating today. So our idea is to first create CAD models of the driver and the driven wheels. These will be individual parts which will be assembled, and we will then be setting up the motion analysis on the assembly. So let's get started with the driver component. So let's click on New from the File menu and select Part. So now before we start sketching the component, we need to make sure that we are in the right unit system. So for all the models that we are going to be creating in the course, we are going to be using millimeters because it's quite easy to provide dimensions for really small features. So to check the current unit system, check the bottom right corner. So you have a drop down. So if you click on that, you see that the current unit system is in meters. So let's just change it to millimeters. Now for sketching, we have three planes, front, top, and right plane, and we can sketch in pretty much any plane we want. So right click on a plane and click on sketch. The other way to reach the same option is to go on sketch and then click on sketch again. So now we need to select a plane on which we need to create the sketch. So let's click on the front plane for now, and we are ready to sketch. So to create the driver, I'm going to first create 3 circles. So let's click on the circle option, and we are going to be selecting the center of the circle, and then we are going to drag it. So we're going to do the process 2 more times so that we have 3 circles in total. Now once I've done this, I'm going to convert the second circle into a construction geometry. So to do that, I can right click on the circle and click on construction geometry. So this makes my circle a construction geometry. So the 3 circles that we have created are blue in color. This means that they are underdefined. An underdefined sketch means that the dimension has not been specified. So let's click on the circle and drag it. You can see that you can change its size. That means it's underdefined. To fix this, you need to provide dimensions. So for this, we are going to go to Smart Dimensions. We are going to select our circle, drag it, and provide the following dimensions of 10 mm. Then we select our construction circle and we provide a diameter of 90 mm. So for the third circle, we are going to give a diameter of 200 mm. So now you can see that all the dimensions have been defined. If you try to click and drag it now, the dimensions are not going to change. So now we are going to draw a line from this point to this point. And we hit escape, and we are going to make this as a construction geometry. So right click and do that. So next we are going to offset this line. So let's click on offset entities and put in a value of 5.5 mm and select the line. So this is going to create a bidirectional offset with cap dents. So bidirectional means the offset takes place in both the directions, and since we have selected cap dents using arc, we see those 2 little arcs on the top and bottom. So when we click OK, you can see that the sketch is fully defined. So we are going to trim off those extra arcs and just select those extras, which is fairly easy to do. Now if you inspect the sketch closely, it becomes underdefined. That's because of this small protrusion. So select that small blue point and the neighbor, click on it and click on merge points. This is going to fix the issue, and now our model is fully defined. Now we are going to pattern the offset that we have created using circular sketch pattern and select the slot that we have created. Make sure that you can preview these slots and enter 5 as the number of patterns and click OK. So you can see that our sketch is still underdefined. So we are going to move the pattern so that we can locate the center for the pattern. So we're going to click that, and we are going to select our origin, and we are going to make them as coincident. So this is going to fix our issue, and our sketch is now fully defined. So now we can trim the extra edges so that we have our slots ready. So now we are going to be creating a couple of construction lines. So let's click on the line tool, select the origin and draw the line as shown, and you can right click and make it into a construction line. Next we are going to create another line, but this time as we create it, you can select for construction to make it into a construction line, select it and draw it as shown. So now these 2 lines are going to have an angle of 36 degrees. So select this line, and type in 36 degrees. So now these 2 lines should have an angle as 36 degrees. Now these 2 lines should be equal in length. So you select one line, hold Control, select the other line and click make equal. This is going to make their lengths equal. So now we are going to draw a unique circle called as a perimeter circle, and we'll be selecting the following 3 points: point number 1, point number 2 and point number 3. And once we click OK, we have a fully defined sketch. Now this needs to be a construction geometry, so let's right click and do that. Now we are going to be creating another circle, so let's go ahead and click on the circle tool and select the center of the first circle and drag it out. Let's assign dimensions to it now. So let's click on Smart Dimension, select this guy and type in 106 millimeters. Next we are going to trim all the extra edges that we have created using power trim, and we are going to just trim off the extra edges, and we are going to make a circular pattern of this new feature that we have created. So let's select the circle, go to circular sketch pattern. We have already selected the entities, and for the number of instances, let's type in 5. And when you click OK, you can see that your sketch is still underdefined. So we are going to follow the same strategy. So we are going to move out our circular pattern, select the center of it and select the origin and click on make coincident. This is going to fully define our sketch. Now we can go ahead with the trim tool and remove all the unwanted edges. Alright, so now we can actually exit sketch, and we have kind of completed the sketch for our first part. So to create a new sketch, click on the front plane and select the sketch tool. So now I'm going to create another circle. So let's start with the circle tool. Select this point and then drag it out to create circle number 1. Let's create 2 more circles as I've done. Alright, so now we are going to assign dimensions to all the 3 circles. So let's click on the inner circle and type in 104 mm, and then select the last circle and type in 10 mm. The outermost circle is already fully defined. So now we are going to create one more circle from the origin, and we are going to drag it till here and assign dimensions for it. So go to Smart Dimensions, click on the circle and type in a value of 201 millimeters. Now we are going to use our trim tool again. So go to Power Trim and carefully trim the edges as I have done. So now we need to convert this into an extruded boss base, but we have one more step before that. So we are going to create a point and we're going to select it here and just click on OK. Now this point needs to be in this particular line, right? So what I can do is I can just select this guy, select this particular line, select this circle and click on make intersection. So that's going to move that point to the intersection of that line and the circle. So by having this as the center, we are going to create a circle, and this is going to be our new spindle. Alright, and let's assign a dimension for it and type in 10 mm. Alright, now sketch 2 is also complete. Alright, now to exit the sketch you have 2 options. You can use the option on the right hand side, or you can click on exit sketch. Alright, so now we are going to extrude from the second sketch. And as you might know, you can use extrude to convert 2D diagrams into 3D representation. So click on the first sketch and hide it. Select the second sketch, and what you're going to do is you are going to go to features and click on extruded boss base and select the features that you want to extrude. So you select the first circle and you put in a value of 10 mm, and this is how much the circle is going to be extruded by. And click on selected contours and select the inside circle so that that part would not get extruded. Next we are going to unhide or show sketch number 2, and we are going to extrude the remaining features. So go to extruded boss base, select this particular curve, and in selected contours select the inner circle, and if you rotate the geometry you can see that the extrusion has actually merged with the previous extrusion. To fix this, there are a couple of options. One, you can type in a value of 20 millimeters so that you can see it, or you can basically use the from option and select surface, and this is the surface from which extrusion would take place, right? So here what you can do is you can provide in a value of 10 mm here, and that should do the job. Now make sure that merge result is selected so that both of our solids would get merged together. Only then would this work for us. We don't want 2 separate solids. Alright, so now we are going to go back to the extrude option again, select our spindle circle, and we are having the same problem here. So we'll go to the from option and click on surface, select this particular face and type in a value of 20 millimeters and make sure merge result is selected and click OK. Alright, so that completes the sketch and also the modeling. So we are going to hide sketch number 2 by right clicking and hiding it, and with that the 3D model of our driver component is complete. In the next video we are going to be looking at how to model the driven component, but before that I need to make sure that I save my part. To save it, click on the save icon, type in save as. I've already created a folder called MBD, and you can just type in a name there. In this case I'm going to type in Geneva driver. Alright, and hit save, and that's basically it. We'll see you guys in the next video. Thank you, bye. Hey guys, welcome to a new video. So in the last video we completed the 3D model of the driver component, and in this video we're going to be looking at the driven wheel. So we are going to start off with a new part. So click on File, New, and Part, and click OK. So next we are going to make sure that we have the right unit system. So let's convert our units to millimeters, and then we are going to select our front plane to do the sketch. So we are going to be creating a few sketches first and then extrude. So let's get started off with the circle tool. Select the origin and draw a small circle, and we'll create 2 more circles. And just like last time, the second circle is going to be a construction geometry. So right click and do that. And now we are ready to assign the dimensions. Click on Smart Dimension. For the first circle we are going to put in 10 mm. For the second circle we are going to put in 90 millimeters, and finally for the third circle we are going to put in 200 millimeters. So now we are going to create a line. So let's click on the starting point, and the ending point is going to be here, and hit escape to exit the line tool. Let's move the dimensions to the left. We are going to convert this line into a construction geometry, so let's do that. And we are going to be creating an offset. Select the line, and we are going to do bidirectional offset, and we are going to use cap ends, and let's make sure that arcs is selected under the sub options, and for the dimensions type in 5.5 millimeters and click OK. So now we are going to create a circular pattern. So let's go to circular pattern, and let's select the entities, and for number of instances we are going to type in 5, and we are going to click OK. Now just like last time, our new sketch is underdefined, and to fix this we are just going to click on our pattern, move it, and select the center of the pattern, select our origin tool, and we are going to select Make Coincident. And this is going to fix the problem. Now we are going to go to the power trim tool, and we are going to trim off the extra edges that is not required. Alright, so our sketch is now fully defined. Now let's create one additional line. Select the first point and select the second point. Now we are going to modify this line so that it is a construction geometry. Right click and do that. Now just like the last time, we are going to create another line, and we are going to make this into a construction geometry as well. Now we are going to be setting up some dimensions. So click on Smart Dimension, select the first line, the second line, and type in 36 degrees. Similarly, select the third line and the second line and type in 36 degrees. Alright, now we are going to select both of our construction lines, and we are going to click on Make Equal. Next we are going to create another circle. So go to the circle tool, click on Perimeter Circle. So we need 3 points, point number 1, point number 2, and point number 3. Once you hit escape, we are going to convert this into a construction geometry, and we are going to select this particular point and draw a normal circle. So select that, drag it out, and create one more circle. Okay, so then hit escape, and now we're going to be setting up dimensions. Click on the inner circle and type in 10 mm, and select the outer circle and type in 106 mm, and then click OK. Oh, actually this particular circle is not required, so I'm just going to delete this. So next we are going to go to trim, power trim, and select the unwanted edges. Alright, and then click on OK. So now we are going to select this curve and go to circular pattern, and make sure that the arc is selected properly, and provide 5 as the number of instances. Click OK. This is going to result in underdefined sketches. So we are going to pull our circular pattern and then select the center of our circular pattern, the origin, and click make coincident. Now click on trim entities, use the power trim, and delete the unwanted edges. So let's click on OK, and our driven wheel is done. So now we are going to extrude the sketch. So go to extruded boss base, select this particular sketch, and you will see that our preview is available right now. Make sure that you put the right distance, and that's basically it. So now we have created our driven wheel, and let's just click on save and save it as Geneva driven. Alright, so now that we have completed both the parts, we are going to create an assembly. So click on file, new, and assembly, and click OK. So this is going to open up a new assembly file. So let's load in the parts. Click on browse and select the 2 parts that you have actually created. So now you can see that the driven component is going to get added automatically, and then the driver. Now in SolidWorks, the first component that gets added cannot be moved. Alright, that's because it's actually fixed. So we are going to first unfix it. So we select the component that was added first, right click, and then select float. So this lets us move the first component. So the second component can be moved by default. Now our objective is to assemble both these 2 components by adding some constraints. So now I'm going to select the front plane of the driver and the front plane of the assembly, and click on coincident, right? So this is what you call as a mate. Mating can be done using another way. You can go to assembly, click on mate, and for example I can just select these 2 faces, the 2 top faces, and I can create a mate. Now I don't want to do it, so I can cancel, right? So what we're going to do is we're going to enable temporary axis. Click on visibility off and select view temporary axis. So this is going to help us visualize these axes. So now let's go to mate, and we're going to select this axis, and in the feature tree we're going to select the top plane, and we're going to coincide this. Then we select the axis again, select the right plane, and do coincidence again. Now we're going to do the same thing for the driven component. Select the axis and select the assembly's right plane and do a coincidence mate. Alright, so we're going to create the next mate. Click on the mate tool and select the front plane of the assembly and the front plane of the driver. Alright, and click on distance mate and type in 10 millimeters, and we're just going to click OK. Now I almost forgot, I don't think I modified my unit system, so let's change it to millimeters. Okay, now you can see that the driver can be rotated about its axis because we have constrained it properly. But the driven mechanism can kind of move in 2D space, right, which is bad, and it can also rotate. So we need to add additional constraints to fix this. Now to fix this, I can select these two axes and provide a distance mate. However, I need to first know what is the center to center distance. So for that, we are going to open the original part file of the driver. So let's click on File, Open, and let's open the driver. So we are first going to enable the sketch that we created. So click on Show, and let's look at the entire model from the front plane. Go to Evaluate, Measure, and we are going to be measuring the distance from this point to this point. So let's select them, and you can see that distance is 111.02 millimeters. So now we can go back to our assembly, and then we can hide this sketch. And what we're going to do is go to Mate. We're going to select the center axis for the driver, the center axis for the driven, and provide a distance mate and type in the distance of 111.02 millimeters and click OK. Alright, so now we can see that the position is almost right, and you can see that I can actually rotate it, and both these components are now quite well constrained. So now what we need to do is we need to make sure that the overlap is not there. So we can just manually move this so that there is a small distance between the two components. So now we can go ahead and disable the temporary axis, and we are almost set to do the motion study, and that would be the multi-body dynamic simulation, and we will be seeing that in the next video. Thank you. Bye. Hey guys, welcome to a new video. So in this video we'll be setting up the motion analysis. So far we have completed the 3D models, and we will be proceeding to the multi-body dynamic simulations. Right now, before we do this, make sure that your assembly is complete, else you will not be able to proceed ahead. Okay, so first make sure that you have SolidWorks Motion installed. Alright, now this will be under the add-ins menu. However, if you don't see SolidWorks add-ins, right click on the menu ribbon, and here you will see a list of options. Now these are the extra add-ons, so make sure that you click on SolidWorks add-ons, and here you will be able to see SolidWorks Motion. So when you select that, the motion study will be enabled. Now in the bottom bar you can see that SolidWorks Motion Study 1 has already been created. Now Motion Study 1 was something that I already created, so let's create a new motion study. Now here you can see that it says animation. Now this is really not useful for us, right? Especially from an engineering point of view. So if you click on this, there is an option called motion analysis, and this is what you want. All right. Now what we are going to do is, in the driver side we are going to add a motor. So to be specific, we are going to add a torque, and that is going to rotate the driven side. So let's add a motor first. So you can see here that there is a motor icon. So let's add a rotary motor. Now we are going to select the center axis for the driver, and you can see that a small arrow appears which tells us how the motor is going to spin. Now click on this arrow, which basically reverses the direction. So this helps you change the direction of the motor. Alright, so now we want the driver side to move in the clockwise direction. Alright, then what you need to do is you need to provide what type of motor it is, right? It could be a servo motor, or it could be a harmonic drive, or it can rotate at a constant RPM, right? So if I click on this, you can see the different types. It's also possible to give an expression. So for us, we are just going to use a constant speed, and I'm going to put in a RPM of 10, right? You can change it to anything you want. You can put it 200, 300, or anything that you want. As part of your challenge, you will be varying it. Similarly, you can provide distance, and you can type in the degrees by which you want the driver should move, and you can also provide a time for it, right? So you're kind of providing the radial velocity The nice thing is after 1000 degrees, the driver wheel is going to stop. Okay. Similarly, there is a start time parameter. So this can be used to basically introduce a small delay, right? If you don't want the motor to start right away, you can provide a delay. For example, if I put in 10 seconds, the motor is going to start after 10 seconds and it is going to go up to 50 seconds. So in our case, we are going to go to constant speed and we are going to type in a RPM of 5. And then let's click on OK. And that basically sets up our motor. Now, what we need to do is we need to establish the contact between the driver and driven component, and only then would there be a force transmission. So let's click on contacts, and what we're going to do is we're going to select solid body contacts and we're going to select these two bodies, and you can provide the material, right? So we are going to be using steel in both the cases and click OK. So right now we've established the torque and we have also established the contacts, right? So now what you can do is you can run this particular simulation. So first make sure that you run it for the selected time. Now you have the calculate option which runs the simulation. You can play the animation from start or you can play it from the current instance. So let's hit the calculate button and this is going to do all the calculation. The spindle is going to enter the slot and that's going to impart a force which actually moves the driven component, right? And then once it leaves the slot, the driven component comes to rest, and this process is going to repeat itself again. Now if you run the simulation longer, you will be able to simulate multiple rotations, right? So after 20 seconds the simulation is complete. Now from the simulation we can extract a lot of outputs, right? So let's just play this one more time to understand how the motion takes place. You can click the play button, you can use the stop button to stop it, and see it at any instant that you want, right? So this is the advantage of a simulation. You can play back things again and again. You can increase the speed. So for example, now I'm actually slowing things down. Now this option is useful if you actually have a very complex motion. Similarly, you can increase the speed to create very fine animations. Now you can also select a loop mode option or a straight playback option, right? So basically after 20 seconds, currently it stops, but if I use a loop mode, then what's going to happen is it's just going to keep on repeating the animation again and again, right? So this is useful in these type of cases where the motion is kind of repetitive. You can also make it play in reverse. This might be useful in some cases. All right, so let's stop the simulation now, and we are going to now extract some useful information from this. All right, so this is what you would call as post-processing, right? So we are going to be generating some useful graphs that can actually help us design this product. So click on results and plots, and we are going to be selecting forces, right? Now you can see that there are other options which you can use, but in our cases we are going to select force, and we are going to be looking at contact forces. There are several forces that are available, but in this case the contact force makes more sense because that would be a very important design parameter. Now we are going to be selecting the magnitude, right? The magnitude of the total force. You can look at components, but in this particular case the total magnitude makes more sense. Then you need to basically select the two components that will come in contact with each other, right? So in this case you can see that I'm selecting only a few faces, all right, and I'm going to hit OK, and you can immediately see that the contact forces appear, right? So here x-axis is time and y-axis is basically the reaction force or the contact force. So now you can move the graph to one corner and hit the play button, right? So the advantage is now you can basically see at which part of the motion the contact forces are exhibited. So this basically helps us fine tune into the component motion, maybe even reduce the speed of the animation so that you can exactly understand the dynamics of the problem. Now you can subsequently take these force values and run a structural analysis calculation with it, but that is not something that we would be focusing on. Alright, so with that I would like to conclude this video. Hope you basically learned how you can actually set up a very simple multi-body dynamic simulation of a Geneva mechanism. We'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. In today's video, we will be learning how to model and simulate a machine vise. A machine vise is a clamping device which is used to hold workpieces. Say that you have to drill a hole or mill a particular component, you can take that component and hold it on the vise and perform the operations. You can also use it for doing simple things such as filing. Now, if you take a look at a vise, it contains several components, but the major parts are the stationary jaw, where the machine vise obviously does not move. That's why it's called stationary. So the stationary jaw is mounted on the base of the device, and you can see that we have also created provisions so that you can screw it on the table or even the machine. Okay, now then you have the moving component, which is called as the moving jaw, right? So you can see that there's a handle that's attached to the jaw, and there's a slider that's connected to the stationary jaw. Moving this is very simple. You can use this handle to move it, and then once you place the component, you just rotate it so that you tighten the component. So our strategy here is quite simple. We are going to first design the individual parts and then assemble them later, and finally run the motion analysis. And I'm going to get started with the stationary jaw, right? So to do this, we are first going to create a new part, right? So let's go to File, New, and open up a new part file. All right, then we are going to be checking our unit system. All right, and as I mentioned in the last video, for this entire course we will be using millimeters, right? So let's just select millimeters, and then we are ready to sketch. So we are going to select the top plane and click on sketch. So then we are going to create a rectangle. We are going to use the center rectangle tool, select the center and then drag it out, then hit escape, and then let's click on smart dimensions to provide dimensions for our rectangle. So the height is going to be 175 mm in height, and the width is going to be 100 millimeters. Now you can see that the sketch is fully defined. So let's exit the sketch. Now we are going to convert this guy into a 3D model. So we are going to use extruded boss base to do this. Now we are going to extrude this by 10 millimeters, which is the default value. So just click OK. So next we are going to be modeling the mounting component. So let's click on the top of the rectangle and sketch on that. Now use the shortcut Ctrl+8 to view this particular rectangle along its normal direction. Then let's use the center rectangle tool and create a small rectangle as shown, and then hit escape. Now let's apply smart dimensions. So width is going to be 30 millimeters and the height is going to be 15 millimeters. You can see that our sketch is fully defined, and hence we are going to exit the sketch. Now we are going to extrude this particular component as well, and this time the distance by which we are extruding is going to be 5 millimeters, and let's click OK. So next we are going to be designing a nut along with a thread. So let's click on the front plane and let's go for sketch. I'm pressing Ctrl+8 to view the geometry along its normal, and we are going to use the circle tool to first create a circle. So make sure that the newly extruded face is kind of a tangent to the circle. So select the origin and the center of the circle and click on make vertical. So this is going to put them along a straight line, and let's say that the diameter is going to be 12.5 millimeters. And as you can see, we need this to be a tangent. So select the circle and select the face and make sure you click on make tangent. So now everything is fully defined. So we are going to now create one other circle which is going to be concentric to our previous circle. So select that and drag it out. Now let's click on smart dimensions, and instead of providing the diameter, we are going to say that the new circle is going to be 1.5 millimeters offset from the old circle. So now our sketch is fully defined, and we are going to extrude this particular sketch as well, and this time we are going to be extruding it using the mid plane option. So from the mid plane, you're going to have 2.5 mm extrusion on one side and 2.5 mm on the other side. So this is our nut. But in order to fully define it, we need to make sure that we create the thread, right? So whenever you have trouble finding a command, go to the search command option on the top and type in thread, right? You can type in any tool that you are trying to find, and SolidWorks is going to tell you where that particular tool is. So we have selected it and just click on OK. Now we need to provide the starting location for the thread. So let us select this top edge, and the end is going to be up to a particular selection. So let's just rotate the component and select the ending edge, right? So this is where our thread is going to be created. Now we are going to make sure that the die type is metric, and for the size we are going to type in M24 cross 2.0, so which is a standard thread. So let's click on OK. When you do this, you might notice that the thread is not getting created. That's because you have not selected the extrude thread option, right? So when you do that, you can see that the thread is getting created. So now we are going to select the line tool, and we are going to draw a line from here to here as shown, and we are going to extend. We are going to keep doing this, and we are going to create 2 more lines. Now to set up the dimensions, we are going to use the shortcut key S. So hit down S and then click on the dimension, select this line and type in a value of 115 millimeters, and select the left line and type in 55 millimeters. Select the bottom line from this particular point to this particular point and type in a value of 150 millimeters, and let's click on OK. So we are going to be selecting and trimming the extra lines. Make sure you use the power trim option and remove the unwanted sketches. Click on OK and exit the sketch tool. So we are going to be converting this into a 3D model as well. So we use the extruded boss base option. So what we are going to be doing is, this time we are going to use the offset option because we don't want the extrusion to be there, and type in a 20 millimeter. Right, so the extrusion is going to be created at a distance of 20 millimeters away, right? And then the extrusion length is going to be 5 mm. So let's click on OK. So now what we need to do is, we need to create the same extrusion on the other side. So what you can do is click on right click, and what we are going to do is, we are going to show the sketch. We are going to extrude the sketch again, but this time we are going to be doing it on the other side. So use the offset method and type in 20 millimeters, but then just reverse the direction, right? So this saves us a lot of time. You don't have to sketch it again and do it. All right. Now let's click on OK. The other thing that I want to do is, I want to create a fillet. So we are going to click on edit sketch, and for this particular feature we are going to be adding a fillet, right? So fillet is nothing but a rounded corner. So we are going to provide a fillet of 5 millimeters at this particular point. Click on OK, and if you exit the sketch, then you will see that this has been changed on the 3D model on both the extrusion, right? So this is very, very handy. If you had created 2 sketches, you have to do this process 2 times, but since we did only once, we save a lot of time. So let's hide this sketch for now. So next we are going to be creating a jaw, right, which is going to be resting on this particular face. So click on this face and click on sketch, and use Ctrl 8 to change the view. So we are going to start off by creating a rectangle first. Use the corner rectangle option. So click on this particular point and this particular point and hit escape. Now we are going to give some constraints here. So we are going to select this small edge and this edge, and we are going to apply a collinear constraint. So they are going to be on the same line. Now we are going to select the center point and the origin, and we are going to select make vertical, and let's click on OK. So now we are going to be providing dimensions by hitting the S shortcut key, and use the dimensions option, and let's select the vertical dimension to be 65 millimeters, and select the horizontal distance and type in a value of 90 millimeters. So now you can see that our sketch is fully defined. So now we are going to apply a fillet to this sketch. So click on fillet and our fillet is going to have a radius of 5 millimeters. Make sure that you select all the 4 corners of the rectangle that we just created and hit OK, and our fillet is going to appear. So everything is fully defined. So let's exit the sketch right now. So now what we are going to do is we are going to extrude this particular sketch that we have created. Extrusion distance is 5 millimeters. Click on merge results and that's it. Now we are going to select this particular face and click on sketch. You can kind of see that we are kind of following a repeated pattern, right? So once you kind of have a good idea of what you want to do, it's very easy to follow. So let's use the corner rectangle tool right now to create a rectangle on the top, and we are going to apply some constraints to it. Now note that there are multiple ways to draw a CAD model. If you're already aware of some basic principles, you can go ahead and follow that. So let's select this line and this particular line and use the collinear constraint, and we are going to do the same thing on the top. So now we are going to define just a single dimension. Use the S key, select the vertical dimension and type in a value of 30 millimeters. Right, there you go, and let's click on OK. So here we are also going to apply a fillet. So click on the fillet tool. You can see that it's already set at 5 mm. So select this point, this particular point, this point, and the last corner, and hit OK. So let's click OK and exit the sketch. So now, as you might have already guessed, we are going to extrude this as well. So this time we are going to extrude it by a distance of 5 millimeters, and make sure that merge result is not selected. Why are we doing this? When you do this, you will be creating 2 separate solids. So now if you click on edit feature and if you click on merge results, you will see that now it's a single solid, right? So this is the difference between using the merge result option and not using it, basically. So we are going to uncheck the merge results so that we are going to have separate solids in this particular case. So now we are ready to save this particular component, right? So we are going to be saving it as a stationary jaw. So please go ahead and save it, and in the next video we are going to be letting you know how to model the moving jaw on the slider. Alright, thank you so much for watching this video. Bye. Hey guys, hope you're all doing good and welcome to a new video. In this video, you will be learning how to model the sliding jaw and the associated components. So this right here is the slider connector which will be mounted with the moving jaw. So click on File, New, Part to get started. Next, we are going to be checking our unit system as usual and change it to millimeters. Select the front plane to get started and click on sketch. Since our moving jaw is in a rectangular shape, we are going to use the rectangle tool, use the corner rectangle tool, pick 2 corners to get started, and we would like to center our rectangle. So select the midpoint of the lower edge and the origin and click on make coincident, and use the shortcut key S to apply dimensions. For the vertical dimension, we are going to type in 115 millimeters. And for the horizontal line, we are going to type in a value of 90 millimeters. Let's click on OK, and we are going to use the fillet tool, and we are going to be selecting the 2 corners of the rectangle, and we are going to type in a value of 5 millimeters. Click OK, and let's exit the sketch. Now we are going to use extruded boss base to convert it into a 3D part, and the extrusion distance is going to be 5 millimeters, and click OK. Now we are going to select this particular face and start a new sketch, and use Ctrl 8 to view this particular face along its normal. Use the corner rectangle, draw it as I have created. Select these 2 vertical lines, make them collinear, and we are going to do the same thing for the top edges as well. Make sure that you're holding Ctrl while selecting multiple lines. Now to provide dimensions, use the shortcut key S, vertical dimension of 30 millimeters, and click on OK. Now we are going to be using the fillet tool to provide a curvature to all the 4 corners, and the fillet radius is going to be 5 millimeters. Click OK. Now to change it, say that you typed it incorrectly, just double click on this and change the number if you have typed it incorrectly. So in this case it's just 5 mm, so let's just go back to the original value. Now we can exit the sketch, and what we are going to do is extrude this guy and type in a value of 5 mm, and make sure that merge result is not selected and just click on OK. Now the movable jaw is ready. So next we are going to be creating the slider. So let's select this particular face, start a new sketch and use Ctrl 8 to view normal to that face. Use the line tool first, click on the line tool, select the first point, select the second point, third point and fourth point and hit escape. So select these 2 points and make sure that you apply horizontal constraint, and let's select this particular point and we want this point to be 10.5 millimeters away from the origin. So select that, apply dimension and type in a value of 10.5 millimeters. And for the horizontal line we are going to type in a dimension of 35 millimeters. Then the vertical dimension is going to be 27 millimeters. So now let's select the midpoint of our top line, select the origin and click on make vertical. So this is going to center our sketch with respect to the y-axis. Now use the offset entities, and what we're going to do is we're going to select this line, the top line and all of them. Now type in 2 mm and you can see that it's basically showing the direction in which the offset is going to be created. So if you click on outside, it's going to be an outside offset. If you click on the right hand side, it would be an internal offset. So now what we are going to do is we are going to create 2 more lines. So let's just select this point and do the same thing here as well. Now hit escape. So next we are going to be applying a fillet to this corner and this particular corner. The fillet radius is going to be 5 millimeters and click on OK. So then what we're going to do is we are going to offset this particular curve. So click on offset entities, type in a value of 2 mm, and what you're going to do is you're going to select reverse direction, right? So it's going to offset outwards, and you can see that the preview also appears. Click OK. Use the line tool to basically close this feature. So line number 1 and line number 2. All right, there you go. So now you can see that it's fully defined. So let's exit sketch and we are going to be using the extrude tool one more time. So this time we are going to type in an extrusion distance of 150 millimeters and click on OK. So now we have created the slider along with the movable jaw. So next we are going to be creating the screw, which basically moves the moving jaw. So I'll see you guys in the next video. Hey guys, I hope you're all doing good. I wanted to notify you guys about a small correction regarding the stationary part. So click on it and then right click and select open part, right? So this is going to open that particular part alone, and in the boss extrude 4 click on sketch 8 and click on edit sketch. So I've typed in the dimensions incorrectly. This 55 millimeters should be 45 millimeters and this 115 millimeters should be 105 millimeters. So this is a small correction. It should be relatively easy to make. Please do that and save your component and use this modified dimensions for your assembly. So let's click on save changes here, and it might ask you to update this component in the assembly. So click on yes for that as well. Hopefully you will be able to make that change easily. I'll see you guys in the next video. Bye. Hey guys, welcome to a new video. Today we will be learning how to model the screw. So if I select my screw, this is what we are going to be doing right now. And if you look at the top of the screw, you can see that it's in a hexagonal shape. So let's click on file, new and part, and click OK. And we are going to make sure that our unit system is in millimeters, and we are going to be sketching on the front plane. So we will be starting by sketching the head of the screw. So we'll use the polygon tool, and we're going to make sure that the number of faces or number of sides is going to be 6. So go ahead and change that to 6, and then select the center and then drag it out, and that is going to create our hexagon. Now we are going to select the top point and the origin and click make vertical so that we align it perfectly, and then click on one particular edge, use the smart dimension shortcut S and type in a value of 10 millimeters. Now that it's fully defined, let's exit the sketch. We'll go to features, extrude this and provide a distance of 20 millimeters. Alright, so that completes the head of our screw. So now we are going to proceed to model the remaining part. So click on this face, create a new sketch, and use Ctrl 8 to view this in the normal direction. Now we are going to be using the circle tool, select the center of the hexagon and drag it out, and we are going to provide a diameter of 9.5 millimeters. So type in 9.5 millimeters for the diameter and then exit the circle tool. So now we are going to extrude this particular circle by 175 millimeters, and let's click OK. So all that we need to do is create the thread on this particular component. So we have to thread on the outer surface of the cylinder. So let's select for thread option. You can see that the option is already there, and we'll first click the starting location for the thread. So we're going to select this lower circle, and for the end condition we are going to be using the blind option. So the blind option basically controls the length of the thread. So we are going to put in a value of 165 millimeters, right? So till the thread length is 165, it's going to continue. And for the size, we're going to type in M16 into 1.5, which is what we provided in the initial video. So let's click on OK, and this process is going to generate the thread. Now go ahead and save this as bench screw.part, and we'll see you guys in the next video. Hey guys, welcome to a new video. So in this video we are going to be modeling the handle or the lever which is going to be used to rotate the screw, and this is the component that we are going to model. So click on File, New, Part, and select OK. So we already know the size of the screw, and since the screw needs to attach with the handle, we basically know what the inner size of the handle needs to be. So let's click on the front plane, go to the sketch tool, use the polygon tool, make sure that you have 6 edges, right? And we're going to select the center, the origin basically, and drag it out. Then just like before, we are going to apply a vertical constraint so that we align the hexagon perfectly. And we are going to select a dimension of 10 millimeters so that it is going to exactly attach with our screw. You can see that it appears as 0.01, and that's in meters. That's because of the unit system. So let's actually go back to millimeters so that we are consistent. When you change the dimension, you can see that our sketch has been exited. So let's go back into the sketch, and you will see that the new dimensions appear. So we are going to create another polygon which is centered at the same location, and we are going to basically select this edge, and we are going to say that the thickness needs to be 5 millimeters. Now let's exit the sketch, and we are going to extrude this particular sketch, and we are going to type in a value of 20 millimeters. Let's click OK. So now we are going to create the handle, and we are going to select this particular face to do it. So let's click on sketch and use Ctrl 8 to view it along its normal. And we are going to be drawing a circle first, and we need to select this point and drag it out. So now we are going to select the origin and the center of our circle, and we are going to use the make horizontal constraint, and we are going to select this point and this point, and we're going to change the dimensions to 10 millimeters. So this way we know that the circle is centered, and change the diameter of the circle to 12.5 millimeters, and click OK and exit the sketch. So now we are going to drag this, and we are going to drag this by 80 millimeters, and let's click on OK. So next we are going to basically create an handle on the other side. So let's rotate the geometry, select this face, click on sketch, and use Ctrl 8 to view it correctly, and use the circle tool, select it, click and drag it out. Now we are going to select the center and the origin, use the horizontal constraint, and then we are going to basically say that the distance between the center and the left face is 10 millimeters. Okay, so this centers our circle, and we can say now that the diameter of our circle is 12.5 millimeters. Okay, so let's click exit sketch, and we are ready to extrude this particular feature. So type in a value of 80 millimeters and click OK. So now we have created all the 4 parts that is required for our assembly. So in the next video we will be taking a look at how to assemble all these components. Alright, I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. In this video, we are going to assemble all the components of the machine device that we have been creating so far. So to start with, we are going to click on File, New, and select Assembly, click OK. And then we are going to click on Browse, and then we are going to select all the 4 components. So let's just select the bench-wise base, and let's click to insert it. And as I mentioned in the last video, when you insert the first component, it's going to be fixed, which means you cannot move it. So to check this out, you can click on it and try to drag it, but it's not going to move. So that is why we are saying that it's fixed. To fix this, or to actually make it unfixed, right click and select the float option. So now you will be able to click and drag or even rotate this particular component. Now we are going to go to Assembly, Insert Components, and click on Browse again. So this time we are going to be selecting the screw component of the bench vise. So now what we are going to do is, we are going to first click on our bench vise base and select its origin, select our assembly origin, and click on coincident. There is another way to do it. So you can basically use the mate option, and you can select the assembly origin and also the part origin, and you can do a coincident mate, right? So but that's just another way to do it, right? Since we have already done it, so let's just hit close to exit out of this option. So next, we want our screw to basically to go inside the nut that we have created. So we are going to go to mate, and we are going to go to mechanical mates, and make sure that you have cleared all the selections. Select screw mate, and first select your faces here, alright, the faces of your thread, and we are going to select another face on the screw. So this is going to basically mate the screw and the nut perfectly. Now what you can do is, you can actually rotate the screw so that it mates perfectly at the desired location. So for example, if you type in 1 or 2 here, then the screw is going to get rotated by 360 degrees, and it's going to proceed into the thread accordingly. If you put in 10, then it's going to basically rotate up 10 revolutions or 3600 degrees, and the screw would proceed in accordingly. Similarly, you have an option to provide a pitch, which is basically the amount of distance the screw travels per revolution, right? So for each 360 degree rotation, it's going to travel 25 millimeters. So let's just click on OK for now, and make sure that our unit systems is in millimeters so that we are consistent. So next, we are going to basically insert the slider, which is mounted on the moving job. So let's basically select the slider and just place it somewhere. Now we are going to be aligning this guy as well, right? So we want this to be inside our stationary component. Now one thing I have forgotten here is to draw a hole on our slider, so we need to create a hole first. So let's right click and click on Open Part. So this is going to open that particular part file, and we are going to add a hole here. So let's select this face, create a new sketch, and then hit Ctrl 8 to view it in the normal direction. And then we are going to use the circle tool, and we are just going to click on the face and drag it out. Now hit Escape, select the origin and the center of the circle, and apply a vertical constraint. Now we are going to use the shortcut key S to provide dimensions. Select the center and the origin and type in a value of 21.25 millimeters. And similarly, the diameter of the circle needs to be 9.5 millimeters. So let's exit the sketch, and what we are going to do right now is we are going to click on the sketch and use extruded cut and type in a value of 5 mm. We do this because we know that the thickness of that particular face or plate is 5 millimeters. So now let us save this particular component and click on S, because this would automatically update this particular component in the assembly. And now if you see here, you can see that our screw appears in the right location. Now initially your slider is not going to match exactly with the screw, so we need to basically create additional mates. So we are going to select this particular face of the slider, and we are going to provide an offset mate. So let's click on mate, and we are going to select this inner face and the outer face of the slider, and we are going to provide a distance mate or an offset mate, and we are going to type in a value of 0.5 mm, right? So this basically aligns our slider along one direction, and then we select this particular face and you can actually move it upwards. So next what we are going to do is we are going to select this particular face, and we are going to select this particular face, and we are going to provide an offset mate again, or a distance mate, and we are going to type in a value of 0.25 millimeters, sorry, 0.5 millimeters. So let's click on OK, and you can see that our screw and slider are kind of moving independently, right? This should not happen. So to fix this, we are going to give a coincident mate. So select this particular face, right? So let's select this face, and we're going to select this particular face. So this way it's going to create a coincident mate, and click on OK. Hit escape, and now if you try to rotate this particular screw, just using your mouse pointer, the slider is going to move automatically, and you can check it in both directions, and you can kind of see that we have assembled it perfectly. The final thing that needs to be done here is to insert the handle. So we're going to click on insert component, browse, and select our handle, and we are going to insert it. So what we are going to do is we are going to select this particular face and say this face, and we're going to click coincident. All right, and we're going to select this particular face and the corresponding face on the nut and use coincident again. Looks like that did not work. Let me select one more face, the side face and the side face here, and click on coincident again. There you go. And finally we select the top faces, do coincident again to align the handle perfectly. So now if you rotate the handle, you can see that the machine wise works perfectly. You can do it both clockwise or anti-clockwise to check this out. With that, I would like to conclude this video. In the next video, we will be learning how to set up the motion analysis. Alright, I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. So now we are in the last phase of setting up this simulation. So before setting up the simulation, make sure that your add-ons are enabled. So you need to first make sure that SolidWorks add-ins is visible, right? So it should be visible in the top toolbar, and click on it and make sure that SolidWorks motion is selected. After doing this, click on motion study 1 and click on this upward pointing arrow, and make sure that you change animation into motion analysis. So now what we are going to do is we are going to put a small motor to basically rotate the handle. So make sure that your axes are visible and click on motor, and we are going to basically select rotary motor. We are going to select the rotation axis, and we are going to provide a RPM of 10 now, and it's going to rotate in the clockwise direction. So click on OK, and this has added the motor. Alright, so the next thing that we need to do is specify contacts. So we are going to select the screw and the nut, and we are going to say that these two parts are going to be in contact, and we provide materials, which is going to be steel in this case. And then we are going to look at the geometry from the front view, and we are going to set up gravity. So we need to make sure that the gravity is along the y direction. All right, and now if you click on calculate, you can see that our handle is actually rotating, and as it happens, you can see that the moving jaw is slowly moving towards the right. Now this happens slowly because we are currently also doing the calculation and rendering at the same time, right? So we will let the calculation finish first, and then we will be able to play it more smoothly. So now what we're going to do is while the simulation runs, we are also going to set up some useful plots that can actually give us the information about the dynamics of the system. So in total, we have simulated the system for about 5 seconds, and since the simulation is now complete, we will be able to play back the animation by clicking on play from start. Now you can see that the animation is much more smooth. You can understand how the different parts actually move. So now at this point, we are ready to make some useful plots, as I mentioned. So we are going to click on graphs, This is going to open up a sub menu, and under subcategory select linear displacement and select magnitude. So now what we're going to do is we're going to select a particular component, and selecting the moving jaw makes a lot of sense, and then click on OK, and almost immediately you get a plot. Here you can see that the variation is almost linear with respect to time, which is kind of understandable because our rotor or motor is rotating at a fixed RPM, right? And since our thread is a fixed pitch thread, meaning the pitch is not varying, the displacement has to be linear, and this kind of checks out. With the plot window open, click on play from start to get a visual representation of where you are in the current simulation and what's the respective displacement. So now let's create another plot. This time we are going to be using something called as trace path to understand how a particular component moves. So click on results, and this time we are going to select displacement. Oops, I accidentally selected forces, so I'm just going to go back and select displacement, and we're going to select trace path, and we're going to select the component which we want to trace. So select this outer edge, and we will immediately see the path that particular edge takes, right? So in order to visualize this, let's look at the geometry from the front view, and when you play the animation you can see how the path trace works. This is pretty cool, right? So now you can see that the plot has actually disappeared. So click on this upward pointing arrow towards the right and select filter results. So this is just going to show the results that have been created. Now what you can do is just move this current plot to the left and expand the results section. You can see both the plots. So just right click and for example, if it's not visible, sometimes just click on hide plot and then right click again and click on show plot. So that basically toggles the plot, and now you can see that it appears. With that, I would like to conclude this video, and we'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. In this video, we will be modeling and simulating the motion of a planetary gear system. Planetary gears are also called as epicyclic gear trains. You will find these type of gears used in automatic transmissions and also in a mechanical lathe. So the planetary gear consists of 4 parts. So you have the sun gear, which is located in the center. As you can see, the sun gear is going to rotate about its own axis. The second gear is the ring gear, as I've highlighted, and this is going to be the housing for the total assembly. And as you can see, the ring gear is going to rotate about its own axis. Finally, we have the planetary gear. The planetary gear is positioned between the ring gear and the sun gear, and as you can imagine, its rotation axis is going to change. Now, in addition to all these components, you can also have a carrier. A carrier is a component on which all the planetary gears are mounted, and in general you can actually provide an input power or take output power from either the planetary gear, the ring gear, or the sun gear. Now before modeling this entire system, we need to talk about gears in general. Now gears are in general identified by the pitch circle diameter and the number of teeth, or the module. If you have any 2 parameters, either the module or the pitch circle diameter, or the module and the number of teeth, you can actually pick the right gear and the third parameter can be calculated. So let me give you an example. Say that you have the module and the pitch circle diameter. Then you can calculate the number of teeth, and here is how it's going to work. Module is nothing but the ratio of pitch circle diameter to the number of teeth. From this relationship, you can actually calculate the number of teeth. That's basically it. Similarly, you have something called as the diameter pitch. The diameter pitch is nothing but the inverse of module. If you're using the metric system, then typically we use a module specification. If it's inch based, then you go for diameter pitch. Now, in order for the 2 gears to mate correctly and transfer power correctly, the pitch circles of both the gears should be tangent to each other. And in addition to this, the module should be the same for the 2 gears. Now we can start by creating our own gears in SolidWorks by sketching and then using extrusion operation. That is unnecessary because SolidWorks provides a library of gears according to different standards, and we can actually use this for our purpose, and that's exactly what we are going to be showing you in this video. Now in this case we need a sun gear, a planetary gear, and also a ring gear, and we can just use the design library to basically import the appropriate models. Now remember, the internal gear is basically an internal spur gear, whereas the other gears, the sun and the planetary gears, are just spur gears, right? So let's actually click on design library and click on toolbox. Now click on add in now, and then you're supposed to select the unit systems. These are the most commonly used unit systems. So we are going to be selecting the ANSI inch standard, and once you do that, you can actually see various components, right? Nuts, pins, power transmission components, O-rings, keys, and so on. Let's click on power transmission. So here you can see chain sprockets, gears, and timing belt pulleys. Since we are interested in gears, let's click on gears, and then you can see that there are 7 types of gears: helical gears, internal spur gear, and so on. Right now, depending on the application that you're trying to model, you can actually choose the right one. So we are interested in the internal spur gear and the regular spur gear, right? So internal spur gear will be used for the outer ring, and spur gears for the planetary gears and the spur gears. Alright, so in the next video, what I'm going to do is I'm going to teach you how you can actually import these individual components from the design library, and how to assemble them, and then finally how to do the motion analysis. Alright, thank you, bye. Hey guys, hope you're all doing good. In this video, we will be showing you how to create the planetary gear systems using SolidWorks. So click on File, New, and then directly go to Assembly. Click OK. Now we are not going to be importing any new parts, so let's just close this. And we are going to get started by importing a ring gear. So let's click on Design Library, and we need to first make sure that we are having the right standard. So go to Toolbox again, and go to the ANSI inch specification, and then click on Power Transmission, and we are going to go inside Gears, and we are going to be selecting the internal spur gear because that's what a ring gear is. So click and drag to actually import the ring gear. You can see that by default a particular gear has been created. Now the reason why we are being asked for a diameter pitch is because we are using an inch standard. Alright, I hope that makes sense, right? So if you have a module in mind, then what you can do is you can just take the reciprocal of it. In other words, diameter pitch is nothing but 1 divided by module, and you can use that value with an inch specification. Now we are going to be setting up the diameter pitch to 1, and for the number of teeth I'm going to be setting it to 32. Now the pressure angle we are going to be using 20 degrees, and for the face width let's put a value of 2 inch. And finally, for outside diameter, we already know that the pitch circle diameter is 32, right? So the outside diameter should be more than 32 for sure. So let's put a value of 38 here. Right now you can see that as we're typing these values, the gear changes, right? So let's just click on OK. Now you can actually import this particular component. Now we need only one copy of the ring gear, so we can just hit escape so that we don't insert a duplicate ring gear. The next component that we're going to create is the sun gear. So the sun gear, as you know, is actually just a spur gear. So let's click on Design Library, click on Spur Gear, and then just drag and drop it. So let's change the number of teeth to 12, and pressure angle is going to be set to 20. Face width, let's go with 2 inch, the same as the rain gear. And for the nominal shaft diameter, we are going to use a value of 8 inches. Now this is nothing but the internal diameter of the spur gear, right? So with that, our sun gear is done, and we just need one copy of it, right? So let's just hit escape so that we don't insert a duplicate one. So now let's get started with the planetary gears. So let's go to the design library and go back to the spur gear. So let's click on the spur gear and drag and drop it. So let's change the number of teeth to 10. Pressure angle is going to be 20 degrees. Face width 2 inch, and the nominal shaft diameter is going to be 5 inches. And then let's click OK. We don't need another copy of the planetary gear, so we are just going to hit escape. So now say that you have accidentally typed the values incorrectly. So let's just click on any particular gear and click on edit toolbox properties, and here you can go back and edit, for example, the number of teeth, the pressure angle, or the diameter pitch. So let's go back to 10 because that's what we need in this case, and then let's just click OK. Now in order for us to position all the gears correctly, we are going to be creating some sketches which can be used to align our gears. So let's click on the right plane of the assembly and then click on sketch. Hit Ctrl+8 to see the plane in the normal direction. Now we are going to be drawing 3 circles, right? And these 3 circles are going to be coinciding with the pitch circle. Now we know the pitch circle diameters of all the components we just now created, so we should be able to provide the exact dimensions. So click on the circle tool and then select the center and drag it out. Now let's click on the circle tool again, and this time we are going to be selecting the origin and drag it out. This is where the sun gear is going to be positioned. Let's create another circle for the planetary gear, so just click somewhere here and then drag it out. We can fine tune the positions later. So now let's assign the dimensions. So for the ring gear, we are going to be having a diameter of 32 inch. So use the smart dimensions, click on the circle and set the diameter to be 32 inches. Now our document is using a MKS system. So what you can do is you can directly type in IN, right? IN stands for inches. So after 32, type in IN, and that's going to set the diameter to 32 inches, and SolidWorks is going to do the conversion internally. So now let's set the size for the circle that represents our sun gear. Now the pitch circle diameter for the sun gear is going to be 12 inches. So you can type in 12 and then IN for setting the diameter to 12 inches. Finally, for the planetary gear, we are going to set in a diameter of 10 inches. So type in 10 and then IN and click OK. So you can see that 2 of our sketches are actually constrained, and for the planetary gear, the sketch is not constrained. Now, as I mentioned before, in order for efficient power transmissions, the modules need to be exactly the same, right? And also the pitch circles should be tangent to each other, right? So what we are going to do is we are going to select the center circle and the circle for the planetary gear and click on tangent. The sketch is still not completely constrained, so let us select the center of our planetary circle and the sun circle and then make horizontal, right? So this is going to constrain all the sketches. When you do this, you can see that a tangent constraint is automatically applied to our planetary and the ring circle, right? That's because we have given the dimensions consistently. So let's exit the sketch. So now we can move on with the assembly. As we have mentioned before, the first part that gets imported is going to be fixed, right? Which in this case is our ring gear. So we need to make sure that we select our ring gear and then click on float. So this way we can actually move our ring gear around. Now what we are going to do is we are going to select the outer circle for the ring gear and the sketch that we created and click on concentric. That's going to align both of them. We are going to apply the same concept for our sun gear first, right? So let's click on the sketch first and then the edge of the planetary gear and click on make concentric. And lastly, we do the same thing for our planetary gear. So make sure that you're actually pressing the control button while selecting both the 2 edges before you make them concentric. So now you can see that we have aligned them correctly, but that's only in the front view. We still need to push back our gears so that they are all in the right plane. So what we are going to do is we are going to select the top face of the ring gear and click on the assembly's right plane and then click on coincident. And we are going to do the same thing for the other gears, right? So make sure you select the right plane, click on coincident, and finally you do the same thing for the planetary gear. Click on the face, click on right plane, and then click on coincident. So what I can do now is I can just hide the sketch because I no longer need it. Now remember, you are just hiding it. For some reason, say that you want it back, you can click on the sketch again and then click on show. Now we are going to hide it because we really don't need it. Now if you have done the assembly correctly and then if you have set up the mates correctly, you should be able to rotate all these components as I am doing right now, right? We have constrained it in such a way that there is no translation, it can only rotate. So for example, I can rotate the planetary gear, I can, if I select the sun gear, I can rotate that, and so does the ring gear. Now let's take a look at the geometry from the front plane. And what we're going to do is we're just going to move it by visual inspection, and so in such a way that they don't intersect. Similarly, let's rotate the sun gear so that all the three gears are not intersecting at all. The next step is to actually assign gear mates. By assigning gear mates, we are telling SolidWorks that, hey, these two particular gears are connected. So if I'm applying energy in one of them, that energy or power is going to be transmitted. So to do this, go to assembly, click on mates, and then go to mechanical mates. And when you do this, you need to be selecting the faces that we want to mate. So let's first select the internal face of the sun gear and the planetary gear. So to do this, select this particular face. A small pop-up with the text teeth/diameter shows up, which means you can provide one of them, right? So in our case, we know the number of teeth, right? So what we are going to do is we are going to provide that as the input. So click here and type in 12 teeth. And for the planetary gear, type in 10. And then we are just going to hit OK. Now we have established one mate between the planetary and the sun gear. So we are going to do the same thing between the planetary gear and the ring. So let's select these two faces, and let's make sure that we select the gear mate and type in 10 for planetary, and for ring gear type in a value of 32. Once you do this, click OK. So now we have established all of our mates. So if you put the model in the front view, and if you just click on any of the gears, and if you try to move it, then it's going to rotate as expected. So let's click on move component, and we're going to select standard drag. And if you move the ring gear, you can see that the planetary and sun gear moves correctly. And then we can set up collision detection if you want to stop the motion of the component once collision has been detected. The final option is physical dynamics. So what physical dynamics is going to do is it's going to translate the forces that we are providing while rotating one of the gears to the other components. So this is very useful to make sure that your assembly is set up correctly even before you run the motion analysis. So in our case, everything looks fine. So let's just exit out of this tool, and we are ready to set up our simulation. All right. So let's click on motion study, and we're going to just expand everything, and we need to make sure that we select motion analysis. However, we don't see it right now. So what we need to do is we need to go to SolidWorks add-ins and then make sure that SolidWorks motion is selected. So now we can go back, select motion analysis, and our strategy is quite simple. We are going to rotate the sun gear, and this motion is going to be transferred to the planetary gear, and from planetary gear to the outer gear. So click on motor, and we are going to be selecting the sun gear. So we need to make sure that we select the respective axis. If axis is turned off, click on show temporary axis, and then we should be able to select that. Now we are going to rotate this at 10 RPM and click on OK. So the next thing that we need to do is set up contacts, because that's basically how gears work and how they transmit energy. So let us select this particular face, and then for material, we are going to say that, hey, we're going to be using steel because that's what we are assuming our materials to be. And then let's click on OK. Similarly, we need to set up another contact pair between the planetary gear and the outer gear. So let's select both of them, and we are going to apply the same material in this case as well. Click OK when you're done. So now our simulation is set up, and we are ready to run this. So let's just click on the calculate button, and you can see that the motion is calculated perfectly and the gears have started moving. With that, I would like to conclude this video, and I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good, and welcome to a new video. Today we will be learning how to model and simulate an entire piston and crank assembly. Basically, we are trying to model a slider crank mechanism, and it's popularly used in a lot of applications to convert translation motion to rotation motion and vice versa. Now there are a lot of engineering applications that use this particular mechanism. For example, IC engines, radial engines, and also reciprocating compressors. The first component is your piston, and the piston is going to be constrained so that it just moves up and down along a particular axis, which is the piston axis. Finally, we have the connecting rod, which basically connects the piston and the crank, right? And because of this connection, the connecting rod is going to have both translation motion and it's also going to be rotating, right? So in this entire assembly, the connecting rod is the one that's going to have the most complex motion. Alright, with that I would like to conclude this particular video. In the next video, we'll start the modeling process. Thank you. Bye. In this video, we are going to get started with piston design. So let's first create a new sketch, right? So let's click on new and then new part, click OK. Then we are going to make sure our unit system is set to millimeters. Now we are going to select the front plane, click on sketch. So we are going to get started with the line tool, click and then drag out the line and then drag it out vertically as shown, and we are going to basically create a profile first and then we are going to rotate it. Now use the 3-point arc, select the first point, the second point, and finally we are going to have another point somewhere here. Now hit escape. Now use the shortcut key S to assign dimensions. Let's select this particular line and type in a value of 101.3 millimeters. And select this line and type in a value of 7.35 millimeters. Select this particular line and type in a value of 6.35 millimeters. And then we'll select this particular line and type in a value of 19 millimeters. And we're going to select both these 2 points and say that the distance between them is 7 millimeters. Next, we need to make sure that this point is 63.5 millimeters away from the origin horizontally. So select these 2 points, drag it out and type in a value of 63.5 and then hit OK. Now we need to set dimensions for the 3-point arc. Let's put in a value of 244.6 millimeters. Now we have fully defined the sketch, so now we can exit the sketch. Now we are going to be revolving this particular profile. Click on revolve and we are going to select the axis of revolution. We are just going to select this particular line, and that's basically the outer shape of our piston. Click OK and you can see that our piston has been created. Now we are going to be creating the slots for the piston rings. So we are going to select the front plane and then we are going to create a new sketch. Use the Ctrl+8 shortcut key to basically align the view. So we are going to be using the rectangle tool and just click and drag it out to create a basic slot. Now let us set up the dimensions for the rectangle, right? So it's going to be 5 mm long and 2.5 mm wide. Use the S key to assign the dimensions. So type in a value of 5 mm for the height of the rectangle and a value of 2.5 mm for the width. Now this particular base is going to be at a distance of 5 mm above the origin. So let's type in a value of 5 mm to position it correctly, the vertical direction. Now we're going to select the end line of the piston and our slot, and we're going to use make collinear so that we align the slot correctly. So now you can see that the groove has been fully defined. Now what we can do is we can use the revolve cut option to basically create the slots. We need an axis for doing this, so let's create a vertical line which will be used as an axis of rotation for the cut operation. Hit escape. Now this line is only for construction purposes, right? So we need to right click and then we need to click on construction geometry, right? And let's exit the sketch. Now let's go to revolved cut, click on it, and you can see that all the selections have been made automatically. Basically the axis of revolution and the profile that is going to be cut out have been selected. Now we need more slots, so we don't have to go through the process of sketching again. We can just use the linear pattern option, and we are going to select the extruded cut, and we are going to make sure that along the Y direction we make multiple copies of this extruded cut. We are going to be using the top plane to achieve this because the top plane has a normal along the Y axis. Now you can see that it has created a few slots, but this is in the incorrect direction, so let's reverse the direction first. And now you can see that the slots appear in the right position. Now we need to type in a value of 10 mm, but that's the value that's already there, so we don't have to change it. And we have 3 instances, and let's just click on OK to create our slots. Right, the final thing that we need to do is create a hole through the piston so that we can insert the wrist pin. So let's go back to front plane and click on new sketch, and we are just going to draw a circle, right? So let's use the circle tool. Let's click and drag it out, and then we are going to hit escape. So we are going to use the shortcut key S to assign the diameter of the circle as 25.4 millimeters. We are going to select the center of the circle and the origin and type in a value of 40 millimeters, which is the vertical distance. Now you can see that the circle is kind of moving radially, right? So we need to constrain that. So we are going to select the center point and the origin and hit make vertical. So now our sketch is fully defined. Now let's exit sketch. Now we are ready to make the cut. So let's select the extrude cut option, and you can see that our circle has already been selected. By default it's using the blind option, which is going to cut only in one direction. We can use the mid-plane option to basically cut on the both sides. Now since we know the exact dimension, we know that the radius is 63.5 mm for the piston, right? So we can just multiply this guy by 2 so that we can cut it from left to right completely. The other option is through all and both sides, right? So this means it's going to cut all the way on both the sides so that you don't have to provide any value. This is going to be quite convenient, and you can see that in this case we have created the cut perfectly. Now we are going to go to the right plane now, and we are going to create a new sketch and use Ctrl 8 to look at it in the right direction. We will be using a 3-point arc now, and let's just click it here, here, and finally here. We are basically trying to provide a shape for the bottom of the piston. Now we are going to provide a dimension for this arc, so let's select this particular point and this particular origin and type in a value of 42, right? Then we are going to select the arc and provide in a value of 45 mm for the radius. Then we are going to select this point and this point, and we are going to click on make horizontal. And finally we are going to select the center of the arc and the origin and hit make vertical. This is going to fully constrain our sketch. Now we can exit the sketch. Now we are going to select the shape and we are going to make an extruded cut. So let's click on that, and we want to basically cut on both sides, so we can just use through all both, and that's just going to cut on both the sides. While using this cut option you need to be a bit careful, because you see that the flip side direction is selected to outside. This means anything that's actually outside of the profile that we selected has been cut out. Now we kind of want the opposite, right? So what we are going to do is we are just going to click on flip side to cut, right? So this way anything inside our profile is going to get cut. So now if we hit OK, you can see that the cut looks like what we want. Now these sharp corners needs to be rounded, so let's use the fillet tool, and we are going to be selecting this particular edge and this particular edge and this one and also this one, and let's just click OK. We are going to leave we are going to fillet it at the default radius. Now for the gudgeon pin or the wrist pin, we already have a groove, but we need a mount, right? So when the wrist pin is actually placed, it needs to basically be sit somewhere, and that's the mount. So we're going to go back to the front plane, and what we're going to do is we're going to select this particular circle and we're going to click on convert entities. This is going to create a circular sketch in our front plane. Now we are going to offset this particular circle at a distance of 2.5 millimeters. So let's just click on the circle and type in a value of 2.5. So this is just going to create another circle, and then let's click OK. Then we are going to exit the sketch. So now we are going to extrude this particular shape. So let's click on extrude, and you can see that it's starting the extrusion from our circle. So let's use the offset option so that the extrusion starts at a distance of 30 millimeters from our original profile. Right, so you can see that that's where the extrusion starts from. Right, and then we want to make sure that the extrusion takes place up to a selected surface, which is nothing but the inner face of the piston. Right, so what we're going to do is we're going to just select the outer surface, sorry, not the inner surface, the outer surface, and you can see that this produces the result, but it's kind of in the opposite direction. So click on flip, and now if you actually hit OK, and if you take a look at the mount, it looks perfect. Now we need the mount on the other side as well, and it makes a lot of sense to just mirror this. So let's go to the mirror tool, and we are just going to select our front plane, and about the front plane, this particular feature is going to be mirrored. Right, and you can see that the right feature has been selected. Just click OK, and you should see a copy of the mount on the other side. Alright, that completes the modeling process of the piston. Go ahead and save the particular model, and I'll see you guys in the next video. Thank you. Bye. Hey guys, hope you're all doing good. In this video, we are going to be showing you how to create the geometry for the connecting rod. So to get started, let's create a new part. So click on File, New, and then click on Part and click OK. Then we are going to make sure that we are having a millimeters based unit system, and then we are going to start by creating a sketch on the front plane. So we are going to use the circle tool. Click and drag it out, and click one more concentric circle, and we are going to draw two more circles, maybe slightly away from the first two circles. We can set up the distances later. Now we are going to assign the dimensions. Use the shortcut key S, select the inner circle, and type in a value of 25.4 millimeters, and then click OK. Let's select the outer circle, and we are not directly specifying the diameter, we just provide the offset distance of 10 millimeters. Now the center for the other two circles are going to be situated at a distance of 212.5 millimeters. Now we are going to select the inner circle on the other side, and this is where the crank is going to be located. So let's just click on that and type in a value of 43.75 millimeters. And as far as the outer circle is concerned, let's provide an offset distance instead of specifying a diameter, and put in a value of 20 millimeters. The sketch is still underdefined, so what I'm going to do is I'm going to select the center of this particular circle and this circle and hit make horizontal. So now our sketch is fully defined. Now we are going to basically draw two lines right now. So let's just click here and maybe drag it out till this particular point, and let's hit escape. Now we are going to say that the starting point of this particular line, so basically this point and this point, are at a distance of 14.1 millimeters. Right, so we are specifying the height, and similarly on this side we are going to say that the distance is going to be 21.45 millimeters. Now we are going to mirror this particular line. So click on mirror entities, and let's select this particular line, and to select mirror about, we are going to be selecting a plane, and let's select the top plane, and that's going to create a mirror copy of the line, and let's just click OK. Now we just need to trim off the unwanted parts, so let's go to trim entities and just trim this and this, and let's click OK. Now we're going to use the shortcut key L to create a particular line, and we're going to click a line like this, hit escape, hit L again to use the line tool, select here and select here, and hit escape, and we're going to use the trim tool again, and then let's cut this particular portion. You can see that we almost got the shape of our connecting rod. Alright, so before we extrude, let's actually add a fillet for our particular components, and let's select this point and this point and this point and finally this point, and we are going to provide a value of 20 millimeters for the radius and click OK. Now let's exit the sketch, and we are ready to extrude this particular shape. Let's click on extrude boss base, and we are going to be using the mid plane option, so let's make sure that we select that, and then for the distance we are going to type in a value of 30 millimeters and click OK. This is going to create the top half of our connecting rod. Now we are going to be drawing grooves so that we can assemble the piston end cap. So let's select this particular face and click on sketch, hit Ctrl and 8 to view the sketch correctly. We are going to use a circle tool, click and drag it out, and let's hit escape. We are going to select the origin and the center of the circle and apply the make vertical constraint, and then we are going to apply the dimension, the diameter for the circle, and put in a value of 20 millimeters. You can see that the sketch is fully defined. Click on OK, and we are going to be drawing an horizontal line, and we are going to be mirroring the circle that we created. I'm using the shortcut key L to draw the line, and this particular thing needs to be a construction geometry, so let's change that, and we are going to mirror the circle as I said. So let's go to the mirror entities tool, and we are going to select the top circle, and the mirror about is going to be the axis. Oh, oops, did it incorrectly. Let's delete the line and add it here. You can see that a preview appears, and there you go, we have mirrored it successfully. Now we can exit the sketch, and we are just going to apply extruded cut. So first let's use extruded boss base and type in a value of 30 millimeters, and let's reverse the direction, and then let's hit OK. Now we are going to be creating a groove cut on this particular face so that we can apply bolts later. So let's click on sketch in this particular plane, hit Ctrl 8 to view it in the right direction. And what we are going to do is fairly simple, right? So we are going to first select this particular sketch, and we're just going to click on show. Looks like it's there, but for some reason it's not visible. So we are going to draw a circle. Even though our circle is not visible, we should still be able to select the center of the circle. So let's just find that out, and we are just going to click there and just drag it out, and we are going to provide a diameter to this circle. Let's type in a value of 11.25 millimeters. Now we are going to mirror the circle just like before, and for entities to mirror, let's select the circle, and we are going to mirror about the top plane. So let's just click on the top plane and click on OK. Let's exit the sketch, and now we are going to be applying extruded cut. I know that last time I said extruded cut, but we actually did extruded boss base. I hope that makes sense. So let's type in a value of 30 millimeters for the extruded cut, and you can see that the cuts are complete. So this is where the bolts would be going in. Now we can hide the unwanted sketches. Let's just click on hide. Alright, so with that we have completed the major half of our connecting rod, right? So in the next video we'll be looking at how to create the end cap geometry. Thank you, bye. Hey guys, hope you are doing good. In this video I'm going to be showing you how to create the end cap and the gudgeon pin geometry. So we are going to get started with a new sketch on a new part. So let's click on File, New Part, and then click OK. Make sure that you're using a millimeter based unit system, and let's click on the front plane to create a new sketch. We are going to get started by creating two concentric circles with the origin as the center. So let's click and drag out the first circle, click again and drag out the second circle. Now we are going to be assigning dimensions. Use the shortcut key S to assign the dimensions. Select the inner circle and type in a value of 43.75 millimeters. Now we are going to provide an offset distance between the inner circle and outer circle and provide in a value of 20 millimeters. So then we are going to create a new line, right? You can use the icon or use the shortcut key L, and we are going to be creating something called as the midpoint line. So we select the center and drag it out and hit escape. Now we are going to be using the trim entities. Make sure power trim is selected, right? And then just cut out the left hand side. And let's click OK, and we can exit the sketch. Then let's exit the sketch, and we are going to go to extrude boss base, and we are going to put in a value of 30 millimeters using the mid plane option so that it gets extruded on both sides equally. And then let's click on OK to finish this operation. Now we are going to select this particular face, and we are going to make some additional sketches on this particular face. So let's click on this guy, click on sketch. Use the shortcut key Ctrl 8 to view it normally. And what we're going to do is we are going to use the circle tool first. So let's circle tool from the GUI, or you can hit S and then click on circle. So let's select this particular point as the center, drag it out like this. Now we are going to select the origin and the center of circle, and what we are going to do is we are going to apply a vertical constraint. Now let's assign a dimension to the circle. Let's click on it and type in a value of 20.5 millimeters, and then make sure you click OK. You can see that the circle is fully defined. Now we are going to mirror this particular circle. Click on mirror entities, and let's select this particular circle, and we are going to be selecting the top plane for mirror about, and then let's click OK. Let's exit the sketch. Now we are going to use extruded boss base. Select the two circles and type in a value of 30 millimeters. Now the direction needs to be reversed, right? So what we are going to do is we are just going to flip the direction, and then let's click on OK. Now the final thing that we need to do is just create the holes so that we can connect this to our main connecting rod. And so let's click on the sketch and then click on show. You can see that the sketch is not there, but if you look really close, you can see it in a light grayish color. Let's create a sketch here and use Ctrl 8 to view it along its normal. And we are going to create one more circle which is centered about the previously drawn circle, right? So let's select that. Make sure that you kind of move your mouse around till you're able to get that center. Drag it out and use the shortcut key S, and we are going to click on dimensions and select the circle and type in a diameter of 11.25 millimeters. Now the only thing that we need to do is mirror this particular circle. So let's go to mirror entities. Let's select this particular circle, and for mirror about we are going to be selecting the top plane, and then let's click on OK. Now let's exit the sketch, and we are ready for our extruded cut operation. By default the distance is 30 millimeters, which is correct. You can use through all option if required. So, and let's just click on OK, and that completes our end cap. Now we are going to hide the unnecessary sketches, so let's just hide it. Alright. Finally, the only thing that we need to do is apply some fillets. So let's go to the fillet tool and click on it, and then we are going to select this particular edge, and you can see that the fillet radius is a bit too much. So maybe type in a value of 5 millimeters, and that looks not that good. Maybe reduce it a bit more, maybe something like 2.7 mm, and that looks more reasonable. right? We are going to do the same thing on this particular edge, but you can see that fillet is not going to work out. So first let's apply the fillet that we have already created, and then maybe we can just create the other edges for which the same fillet needs to be applied, right? And then what we can do is to get our previous edges, we are going to go back to the fillet tool one more time, and let's select this particular edge and also this particular edge. And it looks like this time it's actually showing up for the same radius, 2.7 millimeters. So you know what, guess it worked. So let's just click OK and finish our fillet operations. Right, so that concludes the modeling process of the end plate. So let's just save this guy, and what we are going to do is we are just going to start modeling the gudgeon pin. So you can call this as the end cap, and we'll get started with the gudgeon pin next. So we are going to get started with a new part. So let's click on File, New Part, and then let's click OK. And as always, we make sure that our unit system looks correct, and click on New Sketch. The gudgeon pin is fairly easy to draw. It's basically a cylinder, right? So what we are going to do is we are going to start with the circle tool, and then we are going to create a circle, and then we are going to extrude it. So we are going to use the shortcut ES, click on circle, select the origin, drag it out, and then let's click on one more circle, drag it out. Now we are going to click S, use smart dimensions, and for the outer cycle we are going to type in a value of 25.4 millimeters, so that's 1 inch. And for the inner circle, we are not providing a radius, but we are providing an offset distance, and we are going to type in a value of 7 millimeters. Oh, actually this should not be 7 millimeters. Let's just modify this to 5.5 millimeters, my bad. Let's click on OK, and then you can also exit the sketch. Now we are just going to extrude this sketch. So let's go to extrude at boss base, and we are just going to type in, and you need to make sure that you're using the mid plane option so that it gets extruded on both sides, and type in a value of 127 millimeters, and then click OK. Then what we are going to do is we are going to apply chamfers for both these two edges. So to make a chamfer, click on this little drop down icon right next to fillet and select chamfer, and we are going to select this guy and type in a value of 2.5 millimeters, and we are going to select this particular edge as well, and let's just click on OK. Right, so with that, we have completed modeling the end cap and also the gudgeon pin. So you can go ahead and save this particular model, right? And then in the next video, what we are going to do is we are going to be looking at how to model the crank. All right, thank you for watching this video, and I'll see you guys in the next one. Bye. Hey guys, hope you're all doing good. In this video, we are going to be modeling the final part, which is the crank. So let's get started with a new part and click on OK. Next, we are going to make sure that our unit systems are correct, MMGS, and looks like that's set up correctly. Then we are going to be selecting our front plane to start the sketch. Next, we are going to get started with a 3-point arc. So let's click here, here, and here. So one is above the origin and the other one is going to be below the origin. So let's select the center of the lower arc and the origin, and click on make vertical. We are going to do the same thing for the upper arc as well. So next we are going to be drawing two lines, one from here to here, and the other line is going to be from here to here. So next we are going to select this point and this point and hit make horizontal, and we're going to do the same thing for the bottom 2 points as well, and then let's click OK. So now we are ready to set the dimensions. Use the shortcut key S, click on smart dimensions, select the first circle, select the center of the first arc and select the center, and then type in a value of 45 millimeters. Then we are going to set up the total horizontal distance for the first arc as 80 millimeters, and then the length for this particular line is going to be 120 millimeters. Then we are going to select both these 2 points and type in a value of 60 millimeters. Finally, we have to give the radius for the upper and lower arcs. So for the upper arc, we are going to provide a radius of 50 millimeters. And for the lower arc, we are going to type in a value of 65 millimeters for the radius. So now you can see that the sketch is fully defined. So we can exit the sketch. Now we are ready to extrude this particular sketch. So let's select this guy and type in a value of 20 millimeters and then click OK. So now we are going to select this particular face and start a new sketch. Use Ctrl+8 shortcut to see it correctly. And we are going to start by creating a circle. So this is where the connecting rod is going to be mounted. Click on yes, use the circle tool and click and drag it out. Now we are ready to provide the dimension. So let's first select the center and center of the circle and type in a value of 50 millimeters. And for the circle, let's provide a diameter of 43.75 millimeters. Then let's apply a vertical constraints for the line coming between the center of the circle and the origin. Now let's exit the sketch and we are ready to extrude this particular circle and type in a value of 16 millimeters and we can click on OK. Now on the back side, we are going to create a new sketch and we are going to hit Ctrl+8 to start creating the sketch. We are going to get started again with the circle tool and then let's click the origin and then just drag it out. And let's assign the diameter of the circle to be 35 millimeters and let's click OK. And then we can exit the sketch. And then you can use extruded boss base and type in a value of 20 millimeters. Let's click on OK. So next we are going to be applying fillets to the 4 corners of our crank. Right now the fillet can be done through the sketch or also on the 3D part. So let me show you how to do it via the sketch. So let's click on edit sketch and use Ctrl+8 to view it correctly and then use the fillet tool, right? And we are just going to select this corner, this one and also the bottom 2 corners. And type in a value of 25 millimeters for the fillet radius and then hit OK. Now we can exit the sketch. So now we are going to select the right plane to create a new sketch that will help us cut the crank in a desired way. So we are going to be using a 3-point arc for doing this cut. So let's select this as our first point. So let's select this as the first point, the second point and the third point somewhere here. Hit escape and now it's time to assign dimensions for this. So let's select this guy and and let's type in a value of 4.87 millimeters and we're going to provide a vertical dimension of 35 millimeters and then for the radius we are going to type in a value of 50 millimeters. Click on OK and we are going to do the same thing in the bottom of the crank as well. So let's go to 3-point arc one more time. Click here and let's click here and then here. So let's now assign the dimension. Let's select this corner point and this point and type in a value of 5.12 millimeters. Now let's select this point and apply a vertical distance of 50 millimeters. Finally, we are ready to assign the radius value for the second arc, which is going to be 120 millimeters. Click on exit sketch and then we are going to be doing an extruded cut operation. Make sure that you select flip side to cut. And instead of using the blind all option, we are going to be using through all both. So this way the cut is complete on both the sides. And then click on OK. So looks like the sketch contains more than one open contour. So we need to make sure that we edit the sketch. Right. So what I'm going to do is I'm going to be using the thin feature option here and then type in a value of 20 millimeters. And then reverse this particular direction and then click OK to see if this happens. to see if this works. Looks like I did something wrong. So maybe what I'm going to do is we're going to select this again and we're just going to flip it. But it looks like if you flip it, one side works, but the other side it's not going to cut it incorrectly. So I think we need to re-examine our sketch. Let's go back to sketch edit and let's delete this guy and exit, and then maybe try doing the extrude cut only with the first sketch. Alright, so let's make sure that we select through all both and let's click on OK. Alright, so that is complete. So now what we are going to do is we are going to just recreate the sketch in the right plane and hit Ctrl 8 to view it correctly, and let's quickly recreate the 3-point arc as we did before. So we'll select maybe this point first, this point, and then this point. And as we did before, we are going to apply in the dimensions. So sometimes you have to do these type of things, right? The idea is maybe sometimes the order of operations doesn't work out correctly. So make sure that you go by creating the feature one by one if things don't work the way you want them to. So let's apply a vertical distance of 50 millimeters and then type in a radius of 120 millimeters for the arc, and let's exit the sketch and try using the extruded cut operation one more time. We need to make sure that we select through all both, and then let's just flip that side in which material needs to be removed, and then let's click OK, and there you go. So now this is what I wanted to achieve before, but for some reason we had to go through this one by one. Now this is just one side of the crank. To create the other side of the crank, we can just mirror this. So let's use the mirror tool, and we are going to be selecting this circular face about which the mirror operation is going to be created. And then for bodies to mirror, what we are going to do is we are going to select this entire body that we have created so far, and you can see that the preview appears, and make sure that you select full preview and then click on OK. There you go. So that's how we create the crank. Go ahead and save this. With this we have completed all of our parts, and in the next video we will be assembling them. Thank you so much. Bye. Hey guys, hope you're all doing good. In the previous videos we have been creating models for each and every component. Now we will be assembling all of our components before we proceed on to the motion analysis. So to get started, click on File, New, and then Assembly, and click OK. Now we are going to be importing the components. We'll start by importing the crank first. So let's select the crank component and click on Open, and just feel free to position it anywhere you want. And as we have discussed a couple of times, the first component is automatically going to be fixed. So if you just right click on the component, make sure that you select the float option. So next we are just going to make sure that the temporary axis is visible, and then we are going to select our axis of crank and then the right plane, and then click on coincident. Similarly, we are going to select the top plane and then the axis to make it coincident one more time. So then we are going to expand the component and select the front plane of the component, and you're going to select that the front plane of the assembly. You can see that there is some distance. So for now, let's just move the crank, and then we are going to select the front plane of the crank and the assembly's front plane, and then we are going to provide a distance mate. So click this and type in a value of 36 millimeters, and then you can click OK. Make sure that your unit system is in millimeters. So now we are going to be importing the piston, the connecting rod, and the end caps. So let's just select all these components. Make sure that you hit Ctrl while selecting multiple components. So now let's select this particular axis and this axis right here, and make sure that you select coincident. Now move the components and then select the two faces, and then click on make coincident. Right now you can see that the connecting rod is in one piece. Now we're going to select this particular axis and then the axis of our crank pin, and we're going to click on coincident. So then what we're going to do is we are going to basically select one face of that connecting rod and match it up against the corresponding face in the crank, but we are going to provide a distance mate. So let's just select these two faces and provide a distance mate and type in a value of 1 millimeter, right? So this way we are going to position it correctly while having a very small distance between the two faces. Now you can see that the connecting rod does not have the right fillet, and so we are just going to right click and click on open part. So this is a very handy option. Sometimes you have to edit the part on the fly, and this option is useful for that. So let's click on fillet and let's select this particular edge and this particular edge. This one looks like the last one was invalid, so let's just apply fillet radius of 2.7 millimeters to these two edges, and now try selecting the third one. There you go, perfect. And then the last one. Now let's click OK. So now we are going to add one more fillet. So let's just select this particular guy, and then here the fillet radius is not going to be changed, so let's just click OK. Now we're going to save the plot, and then we can exit this part. Make sure that you click on yes so that the changes have been reflected in the assembly as well. So now it's time to insert the gudgeon pin and also the piston. So let's click on open and insert one component at a time. Now we are going to insert the wrist pin inside the piston. So let's select this particular axis and this axis and click make coincident. Now you can see that it's actually moving inside and out. We don't want that. So what we are going to do is fairly simple. We are going to select the front plane of the wrist pin, right? So let's expand the wrist pin, select the front plane, and while holding control, select the front plane of the piston, and then we are going to click on coincident. This fixes the problem, and we are also able to move both of these two components together. Now we need to make sure that the piston moves only along its axis. So what we are going to do is we are going to select this particular axis and this particular axis and click on coincident. Now with this, our assembly is kind of already there, but you can see that it's still choppy. I mean, all the possible motions are there, but it still doesn't look right. So we still need to add some additional constraints. So what we are going to do is we are going to go to the connecting rod and click on the front plane, and we are going to select the front plane of the piston head, and we are going to make them coincident. Now with this, we have kind of locked in the position of the piston, but it can still move or rotate about the gudgeon pin. So what we are going to do is we are going to select the right plane of the piston, and we are going to coincide that with the assembly. So let's expand the piston, select the right plane, and while holding control, select the right plane of the assembly, and then click on coincident. If you don't want to do this, the other thing you can go do is you can click on mates and then click on the right plane of the assembly and the right plane of the piston, right? Both these options are valid, and then click on OK. Now our assembly is kind of complete, so let's just hide the temporary axis, and if we look at this from the front plane, you can see that everything looks correct. So now you should be able to select the crank, and if you manually rotate it, the piston should move in the desired direction, right? And try to just pull it in several directions. Try to pull the assembly apart to make sure that there are no loose parts or underdefined constraints, right? So now our assembly is complete. So what we can do is we can proceed to do the motion analysis. So to get started, we are going to make sure that SolidWorks Motion is enabled. So go to SolidWorks add-ins and make sure that SolidWorks Motion is checked. So click on SolidWorks Motion and just click on this upward pointing arrow and make sure that you change animation to motion analysis. So once we have done that, we are going to enable temporary axis. So this helps us select the crank axis so that we can set up a motor. So let's add a motor first and select this particular axis, right? And you can see that the direction of rotation is shown, and we're going to provide a value of 1200 rpm, and then let's just click on OK. Now this translates to 7200 degrees per second. Now we're going to change the frames per second parameter because we are interested in calculating an output for each and every degree, right? And you can do this calculation fairly easily, and we are just going to type in a value of 7200 because we want an output for each and every degree. Now if we have a smaller value, then there is a chance that you can actually miss the location of maximum and minimum volumes. And also, while we are here, let's just enable precise contact and then click OK. Next we need to establish contacts, so let's just click on contact, and the first contact is going to be between the crank and the end cap. So let's just say that the material type is steel dry and then click OK. Now we are going to hide the temporary axis and we are going to continue with our contact setup. So now what we are going to do is between the connecting rod and the crank, we are going to add another set of contacts. And then we are not going to be changing the materials. The next contact is going to be between the gudgeon pin and the connecting rod, making sure that the material is the same. And the final contact set is going to be between the gudgeon pin and the piston body. Finally, let's enable gravity. Let's say the gravity acts along y-axis. You can see that there's a little downward arrow, and that's basically it. Now let's take a look at the model from the front view and hit on run calculation. Now this process is going to take some time, right? Because we are storing a lot of values per second, so that's why it's a bit slow, right? But that is the reason why we are getting this really nice and smooth looking animation. So now we are just going to click on stop because 3 rotations of the crank are complete. So now what we are going to do is we are going to plot the linear displacement of the piston. So let's click on results and plots, and category, let's select displacement, and for subcategory let's hit linear displacement, and we are going to be measuring the magnitude. So let's select the top face and then let's just click on OK. There you go. So when you do this, you actually get a very smooth looking plot for the displacement. Now based upon the bore and stroke, you can convert it into a volume trace as well. Now if we add a lower frames per second, then we might not be able to capture the maximum and minimum value for the linear displacement. In fact, that is something that you should try out. Put in a value of 25 frames per second, the simulation would run fast, but then the results are not going to look this good. So here you can see that the piston moves about 10 centimeters, right? Which is kind of what we initially planned on. So now what we're going to do is, now the next thing that we're going to do is verify if the crank is actually rotating at the right RPM. So go to plots, displacements, and we're going to be measuring angular velocity. Click on magnitude and select this particular component and then click on OK. Right, you can see that the angular velocity is around 7200. You can see that it's kind of changing a little bit, but if you pay attention to the axis, it is in between 7200 and 7200. Right, so that basically means the RPM is constant. This is something that you need to check because you always need to get the same value that you put into the simulation. Now the other cool thing about this particular software is we can export the plots. So for example, let's just click on this filter results so that we can take a look at only the plots. So let's expand the results and right click on linear displacement, and then you see that there is an option called as show plot. Right, now remember, only when you see the plot you will be able to export it. So when you see the plot, right click again, and this time you can see that there's an option called export to spreadsheet. This process takes a little bit of time, but you should be able to see an Excel which contains the data set. You can use this for further processing if required. You can see that the plots have also been transferred, which is very, very convenient. Alright, with that I would like to conclude this particular video, and I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. Today we will be first modeling the components of our engine valve system, and then we'll proceed to do the multi-body dynamic simulation. So to get started, we're going to work with the cam. So let's click on File and then click on New, and then click on Part and then click OK. Once this is done, we are just going to make sure that our unit system is set to millimeters, grams and second. We are going to use the frill plane to start our new sketch. So let's click on it and view it along the normal. So we are going to get started with a center point circle. Use the circle tool. Let's just click, and then we are just going to drag it out. So let's just click on the origin and then drag it out as shown. Now we are going to create one more circle just above this particular circle. So just click and drag it out like this. Hit escape. So now we are going to basically constrain these two circles to define our cam profile. So select the center points of two circles while holding the control key. Oh, sorry, I selected it incorrectly. So let me just select the centers one more time, and I'm just going to click on make vertical. So next we are going to assign dimensions to the circle. We are going to use the shortcut key S. Once you hit that, make sure that you select smart dimensions. We are going to select the bigger circle and then put in a value of 25 millimeters for the diameter. And for the second circle, let's put a value of 10 millimeters for the diameter. So now what we're going to do is we're just going to move the smaller circle. So let's just click on this guy and click on make coincident so that we basically constrain the sketch completely. So next I'm just going to use the line tool to draw two tangents. So let's first draw the lines first as it is, and once we draw it on the other side, you can select the line tool one more time, and we can draw the line on the other side. Now let's hit escape. To add the tangent constraint, click Ctrl and select the line and the circle and click on make tangent and click OK. And we will be doing the same thing for the other side. Make sure that you use a Control key while selecting both the entities. Let's click OK. Finally, we basically do the same thing for the top circle, right? And make sure that you do it on both the sides. Only then your cam is going to turn out symmetrical. This is an important step, so make sure that you follow this carefully. Just click on OK when you're done. So now what we need to do is just trim unwanted entities. Let's make sure that power trim is selected. And then let's just drag it out and delete unwanted sketches. So now the cam has been completely created, and now it's time to exit the sketch. Now to create the 3D cam, we just need to extrude it. Click on extruded boss base, and you can see the preview appears. So type in a value of 20 millimeters. Actually 20 millimeters is a bit too large. You can see that the cam is quite fat. So let's just go back and change this to 10 millimeters. And to make it easy to assemble, let's use the midplane option. So that way when we are assembling this component, it's going to be much more easier. So now it's time to save this part. Right, so go ahead and save it as cam.prt. Make sure that you're saving all the components of a particular assembly in a single folder so that it's easy to bookkeep. So in this case, I'm just going to call this scam. You can call it anything you want, and that's basically it. So the next component that we are going to be working on is the push rod, which is basically the cam follower. So to get started, let's click on File and New, and we are going to create a new part. Let's click on OK. As always, let's just make sure that our unit system are consistent, and then we are going to select our front plane to start our sketch. So here we are going to get started by drawing a few lines. Use the line tool, and just click here and then just drag it out. Try to coincide that with the y-axis and make it coincident with the origin. And then let's drag it out to the left, drag it again to the top, and that basically looks okay. Hit escape when you're done. So then we are going to basically use a 3-point arc tool. So we're going to select this point, and the third point is somewhere here, and then hit escape. So now we are ready to constrain this guy. So let's select this particular point and the center, and let's click on make vertical. Now we are going to add tangency constraint to this particular arc and this vertical line, and click on make tangent. So now what you can do is you can just click on that particular arc, and you can see that the tangency constraint is showing up. So now it's actually time to add dimensions. So click on smart dimension. Let's select this particular line and this particular line, and type in a value of 110 millimeters. And for the horizontal dimensions, we're just going to add a value of 2.5 millimeters. Just zoom in so that you can see it a bit more clearly. So now we can just exit the sketch. Now to create the push rod, we're just going to revolve this guy. Right, so let's select this particular line, which is the axis of rotation, and use the revolve tool, and that's basically it. Click on OK to finish this component. So now it's time to save this guy. So let's save this as push rod. So now that we have completed the push rod, we can move on to our third component. Our third component is going to be the rocker arm. So click on File, New, and let's select a new part and click OK. And as always, make sure that you check the unit system, and then we are going to be using the front plane to start the sketch. So let's click on front plane, click on sketch. So this time we are going to get started with a few lines, circles, and arcs. So let's select the line tool first and click it somewhere here, and draw an horizontal line, and then drag it out again to basically create a vertical and horizontal line, and hit escape. So what we are going to do is we are going to use smart dimensions and add some dimensions here. So type in a value for 10 millimeter for the horizontal line, and the vertical distance is also going to be set to 10 millimeters, and this one is going to be 15 millimeters. So now we are going to create a 3-point arc. So let's select this guy, and we are going to basically select this as our first point. Second point, let's draw it somewhere here, and third point somewhere here. Basically we are trying to draw the rocker arm. There are multiple ways to go about the same thing. Here I'm just following a particular method. Oh, actually before we do that, we need to click on the circle tool to basically create the hole that's found in the center of the rocker arm. So let's click and drag it out, and let's create 2 circles and hit escape. And we are going to assign dimensions to these circles. So use the smart dimensions, and for the inner circle, let's put in a value of 12.5 millimeters, and for the outer circle, put a value of 30 millimeters for the diameter. Hit escape. So let's select the center of this particular circle and this particular point and hit make horizontal. So then let's select this particular point and this circle, and we are going to click on make coincident. Now our circle is fully defined. And finally, let's select this particular point and the circle, and let's click on make coincident. Now for this particular curve, we are going to assign tangency mate. So let's select these 2 edges. So let's the arc first, and then this arc, and then we are just going to click on make tangent. We are going to repeat the same process for these two arcs as well. So let's click on this one and this one and click on make tangent. Now finally we are ready to trim, right? So let's go to trim and make sure that power trim is selected, and then just remove the unwanted parts very carefully. You need to be a bit careful, right? So do something like this and you should be good. Now one last thing, we need to add one more dimension, but I think I forgot a constraint. So what we're going to do is we're going to select this particular point and this particular point, and we are going to click on make horizontal and then apply the constraint. So now we are ready to add the dimensions to constrain all the 3-point arcs. So let's select this top arc and put in a value of 71.5 millimeters. And for the second 3-point arc, we are going to put in a value of 7.5 millimeters. And for the third 3-point arc, we are going to put a value of 47 millimeters. Now let's select this particular guy and this particular guy, and let's put in a value of 75 millimeters. So when you do this, you can see that most of your control arm components or sketches have been constrained. So the final arc is this guy. So let's select these two arcs and we are going to add a tangency constraint. So when you do this, all of your sketches should be constrained. Now to finish off, we are going to be adding some fillets, so basically to round the corners. So let's select this particular point. Looks like the radius is too large here, so let's just make it to 2 millimeters, and let's try to select that corner again. Now you can see that it appears. Usually if you're able to see a preview, you should be good. So now let's select a few more corners and let's just click on OK. Right, so that looks good. Let's click on OK. And with that, the rocker arm part is complete. Now all that is left is to convert this into a 3D component. So let's exit the sketch and we are going to use the extruded boss base tool, and we are going to be using the mid plane tool, and let's put in a value of 20 millimeters and then let's click on OK. So now it's time to save this particular component. Use the shortcut key Ctrl+S and save this as rocker arm. Alright, so the next component that we're going to create is the valve. So to get started, let's click on File, New, and then select a new part file and then click OK. So we are going to be sketching in the front plane, but before that we need to make sure that our unit systems are right. So let's make sure that it's in MMGS. So let's go to front plane now and click on Sketch. So in order to create the valve, we are basically going to start by creating a few lines. So let's select the line tool and then click here and drag it out like this. Click it like this and then just keep dragging it like this. As long as you don't hit escape, the line tool should still continue. So now if we hit escape, what we're going to do is our sketch is done. So we're going to click on Smart Dimensions and set up some dimensions right now. So for the vertical dimension is going to be 80 millimeters and the horizontal line is going to be 10 millimeters. Oops, looks like I typed it incorrectly. So just double click on it and change it to 10 millimeters. And this line is going to have a length of 17.5 millimeters. And select this particular guy and type in a value of 8 mm. And finally, this line is going to have a length of 50.75 millimeters. Sorry, 57.5 millimeters. So now let's click OK. And then we are now going to create some 3-point arcs. So just click on this point. Click here and then drag it out and put it somewhere like this. Let's draw one more 3-point arc. Let's click here and click here. Finally, we're going to select this point and we're going to click maybe somewhere here and finally somewhere here. and hit escape. Now we are finally going to draw a line. So let's select this guy, click here, and then click here. Now if you hit escape, you can kind of see that we have our valve. So now we need to assign some constraints. So let's select this guy and then click on make horizontal. And then just drag this out. Looks like the shape is kind of funny, so we need to select this particular point and drag it out. We'll assign the exact dimensions shortly. So let's just click on this particular arc. It looks like it's currently not tangent to this line, so let's select this line and click on make tangent. Make sure that you have control key pressed when you make the selections. So let's select these two arcs and then click on make tangent. Let's click on OK. So now we are going to use the shortcut key S to assign smart dimensions. So we are going to select this particular line, and we are going to select the top horizontal line, and we are going to hit, and we are going to provide a value of 81.5 millimeters. And we are going to say that the length of this line is 5.8 millimeters. And we are going to select this guy and put in a radius of 35 millimeters. And for this particular arc, we are going to put in a value of 1 millimeters. And finally, select the last 3-point arc and put in a value of 45 millimeters. Now let's hit escape. Now you can see that the sketch is still underdefined, right? So if you just click and drag this point, you can see which are the two things that are underdefined. So let's go to smart dimension. Let's select this particular point and select this origin, the local origin, and then put in a value of 12.78 millimeters. So this way, since that point is constrained, our sketch becomes fully defined. So now for this particular corner, let's round it. So let's go to the fillet tool and type in a value of 5 millimeters to this particular point. Make sure you change it and then click OK. And let's exit the sketch now. Now we're going to revolve this. So before we revolve it, we need to make sure that we select the axis of rotation. So select this particular line first, and then let's go to revolved boss base, and that's basically it. That's our valve. Now let's just click OK to finalize our revolve. And I think that looks pretty good. So let's go ahead and save this guy. So hit Ctrl S and then type in valve or something like valve_engine. So the next component that we need to create is like a valve stem. So that would be the stationary component. So let's create a new component first, or a new part first. And as always, let's check the units. Make sure it's in millimeters, grams, and seconds. And we are going to begin sketching on the front plane. So we are going to select the line tool first, and then we are just going to draw a horizontal line first, and then a vertical line, and then another horizontal line that's slightly smaller, vertical line, horizontal line, and we are just going to complete the shape. Now let's hit escape, and now it's time to set dimensions. So let's click on smart dimensions. Now the length of this particular line is going to be 10.5 millimeters, and this vertical dimension is going to be 10 millimeters. This line is going to be, the thickness is basically going to be 0.5 millimeters. Similarly, this particular thickness is also going to be 0.5 millimeters. Now you can see that the sketch is still underdefined. So what we need to do is we need to provide a distance from origin. So let's select this point and this point and put in a value of 2 millimeters. So you can see that it is still not fully defined. So let's select this point and click on make horizontal. It is still undefined. I wonder why. So what we are going to do is we're just going to click on this point and drag it out. Oh, looks like we need to add a vertical constraint. So let's just click on make vertical. So that way the sketch becomes fully defined. So now we're going to add a construction geometry, basically an axis. So click on the line and use the for construction option and draw a vertical line. So this is the axis about which we are going to rotate this particular component. Let's exit the sketch So we are going to use the revolve tool, and that's fairly straightforward. So let's click on the axis first, use the revolve tool. You can see that it kind of creates the shape perfectly. And then let's just click on OK. So this is our last component. We are basically going to call this as valve mount or valve stem, whatever name you want. Make sure that you save it. Now you can see that all of these 5 parts are still open. The reason why I have that is it's easy to assemble, right? So to go ahead with the assembly, let's create a new file, or actually you can just use file, make assembly from part. That's another option that you can use. So when you do this, you can see that all of our parts are available on the left hand side. So let's just add one part at a time. So what you can do is you can shift and select all the parts if you want, and you can just drag and drop it out. Oops, looks like I did not do it correctly. There you go. So you can see that you can drop one part at a time, right? So just click, and initially don't worry about positioning them. You can just put them anywhere. When we constrain them, everything will fall into place. So it looks like we have imported all the geometry. So now it's basically time to go ahead and assemble. So since the cam is going to be kind of a reference, we are going to make sure that we first float it, and then once we set its position, we will be able to align the other parts correctly. So now we are going to enable the temporary axis. So this helps us, align and assign our mates correctly. So we are going to get started with the rocker arm. So let's select the axis of the rocker arm, the right plane of the assembly, and click make coincident. Select the axis again, and if you are unable to select it, zoom in to make sure you select it properly, and select the top plane and click on make coincident. So then we need to look at where the right plane is for the rocker arm. So let's see, is it in mates assembly? No, not really. It's actually down here. So let's select the front plane and select the front plane of our assembly, and then click on make coincident. So similarly, what we're going to do is we're going to select the front plane of the cam and use Control key and select the front plane of the assembly and click on make coincident. Now let's select the axis of the push rod and Control select the front plane and then click on make coincident. So you can see that we are trying to kind of bring everything to the front plane. So similarly, what we are going to do is we are selecting the axis of our valve, the front plane, and then click on make coincident. Make sure that you are pressing Control key when you're selecting these two components. Finally, we do the same thing for our valve mount or valve stem component. So now we're just going to manually drag the push rod to something like this, right? So let's select this axis and select the right plane, and then let's add a distance mate and put in a value of 20 millimeters, and then click OK. And let's just make sure that the unit system is in mmgs. Now let's just drag out the cam, and then we're going to select the axis of the cam. So let's just zoom in and select the center axis, and let's select the right plane of the assembly and then provide a distance mate and put the same value of 20 millimeters, and then let's click on OK. Now let's drag out the valve guide or the valve mount. Let's select the axis of the valve mount and select the right plane. Make sure Control is selected, and add another distance mate and put in a value of 50 millimeters, and then click on OK. Now let's select this particular front plane and then select the top plane, and then we're going to add a distance mate and put in a value of 60 millimeters. So that's going to be the vertical position of the valve mount. So now you can just drag out the valve, and we should be able to coincide these two axes. So let's select axis number 1, axis number 2, make sure Control is selected, and click on make coincident. Now let's take a look at the geometry from the front plane, and let's just click on this guy and push it. Because of our constraints, it's going to perfectly move in the vertical axis. Similarly, we should be able to rotate the cam and drag it exactly vertically down. Now we are manually setting up the position, so make sure that you see a very small gap, right? So now what we're going to do is, so we're going to select the axis of the cam and the top plane, and we're going to provide a distance mate and put in a value of 127.5. 5 millimeters. So this is going to be the exact distance. Sorry, actually it's just 125. And click on OK. So now if you try to rotate this, you can see that it rotates perfectly. Now what we want to do is we are going to set the system up with the right amount of contact. So what we are going to do is we are going to have a small gap first, and then go to assembly and then go to move component, and we are going to use something called as physical dynamics. So the idea behind physical dynamics is where it basically moves a component till it touches with the other component, and if it does touch, the contact is basically transmitted and it goes to a point where all the components are locked into the right position, right? So this is pretty useful because you don't have to second guess where the exact position of the push rod or the valve mount is going to be, right? So the final thing that we are going to do is we are going to open up the rocker arm and select the top plane, select the top plane of the assembly, and we are going to make sure that we put in an angle mate and make sure it's 0 degrees, right? So this way we know that these two planes are parallel. So I just wanted to check that. So we don't need an additional mate for that. So just rotate the geometry, make sure that everything looks okay. Alright, with that I would like to conclude this video. The next step is to basically do the motion simulation, and we will do that in the next video. Hey guys, hope you're all doing good. So we have actually created the 3D model of our valve, cam and rocker arm assembly. So now we are ready to set up the motion analysis. So to get started, make sure you go to SolidWorks add-ons and then make sure that SolidWorks motion is enabled. So then go to motion study 1, and then we are just going to select this animation and modify this to motion analysis. So what we're going to do is we're going to rotate the cam, right, and we're going to do this by adding a motor. So let's click on motor, and what we're going to do is for the component we're just going to select this particular axis. You can see that the direction appears. Now for the RPM we're just going to put in a value of 1200, and then let's click on OK. So the next thing that we need to do is enable contacts. So let's go to contacts, and then what we're going to do is we're going to select this particular component and this component, and with respect to contact we need to assign materials. So let's select steel dry. So we're going to use the same material property for now, and then let's just click on OK. Similarly, we are going to set up the contacts between the push rod and the rocker arm. We are going to be using the same material connections again, so select steel for both the pairs, and then let's click on OK. Next, it's going to be between the rocker arm and the valve. So let's select that guy, select the valve, and make sure that the material property is the same. Let's go ahead and change it to steel. Now you can try changing this. We are just trying to follow a standard here. In real life, the material is going to be probably different for each and every component. So then finally we need to add a spring. This is called as the valve spring, and this is responsible for the valve to come back. So let's click on spring, and we are going to make sure that we have selected linear spring, and we are going to be selecting two edges where the spring is going to sit, right? So this is one edge, and then this is the other edge, right? When you do that, you can see that you get a preview of the spring. Now this is not the real spring, this is just a preview that SolidWorks generates. Now sometimes you can see that the selection looks a bit weird. The spring might look inclined, but that should typically not affect your simulation, right? So if your spring is inclined, don't worry about it. So that is just for the purpose of preview. Now you can see that the distance, the free length is 35 millimeters. So that's the free length of the spring, right? Now in real life, the spring is actually pre-tensioned, right? That means the spring is compressed a little bit when the valve is actually closed, right? And this pre-tension can be given in terms of a length. So let's change this free length to 45 millimeters. So that means currently the spring is pre-tensioned by 10 millimeters. That's what it means. And to show that, SolidWorks changes the color of the spring to red. Now this is a very important step. If you don't have pre-tension, the valve is going to be extremely loose when it's closed. this is just for graphical purposes. There are options to make the spring better looking. You can change that if you want to. Now I think we are all set, so we should be able to go ahead and run the simulation. So let's click on calculate, and you can see that the simulation runs fine, and you can see that how the cam's motion is transferred through the push rod to rocker arm and all the way up to the valve. So let's just stop the simulation right now, and we are now going to plot the results. So let's click on results and plots, and what we're going to do is we're interested in looking at the displacement of the valve. So let's select linear displacement, and we are going to basically be using the magnitude option, and then let's click on OK, and you can see that the valve profile immediately appears. Now the plot looks a bit weird. It's quite non-uniform, right? Now this is not ideal, right? One of the reasons this is actually happening is the material property has not been defined. So it could be that SolidWorks is internally assuming materials that are not ideal for this type of problem. So what we're going to do is we're going to select everything, right click, and then we're going to select material, and what we're going to do is we're going to click on edit materials, and this is like a comprehensive list, and we are looking for plain carbon steel. There it is, and let's just click apply. But before you do that, you can just look at the material properties, right? If you want, you can change the unit systems, but that's not required in this particular case. And you can see that all the properties are there, so that's one thing you need to check. Sorry, before you select a material, make sure that all the important material properties like density, shear modulus, yield strength, and all of those are specified. Now not all of them are going to be used in the calculation, but it's important to make sure that they are all defined. So once you click apply, hit close. Now the materials would have been applied. Now in order to kind of indicate this material change, the color has been modified. Now if your computer has a good graphics card, you will be able to see this a bit more clearly. So now we are going to make an additional change. So we are interested in getting an output every crank angle, right? So this means you need to change the output frames per second. Now we are going to do another change. We know that our cam is rotating at 1200 RPM, and if we are interested in getting an output at every crank angle, meaning if you're trying to resolve the system so that you get the lift for every crank angle, then you need to increase the frames per second. Now 1200 RPM in degrees per second is going to be 7200 degrees per second. So what we are going to do is we are going to change the frames per second, or the output frequency, by clicking on motion steady properties, and instead of 25 we are going to put in a value of 7200 frames per second. So this is going to capture every crank angle, and once I enable precise contact, I'm just going to click on OK. Now this is going to slow down your simulation for sure, right? Now the other thing we need to do is we don't have to run this for 5 seconds, right? It's too long. So what we're going to do is we're going to modify the end time of the simulation. So to do that, so right click on this particular keyframe and click on edit key time, and type in a value of 0.2 seconds and then click on OK. Now this is going to shorten your timeline, but don't worry, we are going to have 7200 frames per second. Hit calculate. Now click on yes, and then this is going to take a lot of time. You can see that the simulation is very slow, but it's highly resolved. You can see a lot of details. That's because you're providing data set 7200 times a second. And now suddenly you can see that everything has been collapsed, right? And this is happening probably because of the spring stiffness. So now let's just stop this guy, right? And this is happening because of the stiffness being very low, right? And that's because the spring stiffness is set to 1 Newton per millimeter, right? Which is very, very low, right? And that is why the system is kind of getting ripped apart. So we need to make sure that any material property and mechanical property be realistic. So what we are going to do is we are going to modify the spring stiffness for the spring that we have created. So let's right click on the linear spring and click on edit feature, and you can see that this is and we're going to change this to 10 Newton per millimeter. And let's click on OK. And we're going to run the calculation one more time. Right, if the spring is not stiff, then it can easily be pushed in and it's not going to offer any resistance. So now you can see that when we assign the right value of stiffness, it pushes the rocker arm back in the desirable way. Right, so it's very important to add the right mechanical properties and the material properties, to make sure that the results are accurate. Or actually what you will be doing is you will be following this particular video, and then you will be making sure that you get some results. So now we can go ahead and make some plots. So let's go to results and plots, and we're going to select displacement in category, and subcategory we're going to select linear displacement, and we're going to click on magnitude. Now the first component that we're going to select is the bottom face of the push rod. So we're going to see how far that actually moves upward. So click OK, and you will see the plot. Now you can see that this plot is far more uniform, right? So you're getting repeatable lifts, and this is what you need when you are actually making an engine, right? Because if this is not the case, then your intake stroke is going to be completely different each and every time the engine runs, which you don't want. So we're just going to right click and go to chat properties, and we're going to go to title, and let's just uncheck use feature name and type in a value, linear displacement of push rod. Looks like there's a typo. Let me just correct that, and then let's click on OK. Now you can see that the plot has been updated. So we're going to filter our settings, and we're going to go to results, and you can just right click and you can just select the rename option. We're not going to be worrying about it right now. Right, so now next we are going to measure the linear displacement of the valve. So we have already done this before, so right click and click on show plot. When you do this, you can see the valve lift profiles, and you can see that it's highly repeatable, and it looks much better because of the higher frames per second that we have set up. Right, so then we are going to now export these two plots into an Excel sheet. So let's just reduce the size of this particular plot. Now in order for you to export the plots need to be visible. So right click on the plot, click on export to spreadsheet, and if you have Excel installed, and this is automatically going to open up Microsoft Excel, and it's going to show you the data set and also the plot. So let's just give it some time for it to do the conversion and load it in Excel, because there's a lot of data set that it needs to transport. Right, so this is what I'm talking about. So now you can see that the data is completely available in Excel, including the plot. Now what you will be doing is, for your challenge, you will be making multiple plots, but in order to do that, you will be exporting multiple data sets to Microsoft Excel for different operating conditions, and then you will finally be comparing the results in Microsoft Excel. Now in this case, you can see that the entire data set is available, right? So you have about 1640 frames. So, and that is what is being plotted here as well. Alright, so with that I would like to conclude this video, and we'll see you guys in the next one. Bye.